Hello there, and welcome to Science for Sleep, where curiosity slows down, questions soften, and the universe becomes a little quieter as we explore it together. Tonight, you're invited to settle into a gentle line of thought, one that doesn't demand answers right away, but instead allows ideas to drift past like distant lights seen from a moving train. There's no rush here, no finish line to cross, just a calm unfolding of one of the most persistent questions humans have ever asked about the cosmos and our place within it. This evening, we're turning our attention to speed, not the kind measured by traffic signs or racing watches, but the ultimate kind, the speed that shapes how the universe itself behaves. More specifically, we're going to explore whether faster-than-light travel is actually possible, not as a movie plot device or a flashy promise of science fiction, but as a real question rooted in physics, observation, and the sometimes uncomfortable boundaries of what nature allows. It's a topic that has inspired wonder, confusion, optimism, and more than a few headaches for scientists over the past century, and yet it remains strangely personal, tied to our desire to reach, to explore, and to understand what lies beyond what we can currently touch. Before we move any further, take a moment to notice where you are right now. Are you listening from a quiet room late at night, or perhaps from somewhere still humming with distant sounds? What time is it where you are? Is the day just beginning, winding down, or resting in that in-between state where clocks feel less important than breathing? Wherever you happen to be, this moment belongs to you, and you're welcome to let the outside world fade slightly as we continue. If you find this kind of slow, thoughtful exploration calming or helpful, if it feels like a good way to unwind or gently occupy your thoughts as sleep approaches, you're always welcome to like the video or subscribe to the channel. It helps this small pocket of calm reach others who might be looking for the same kind of quiet curiosity. But for now, there's nothing you need to do except listen and let the ideas arrive at their own pace. Now, when people hear the phrase, faster than light, it often brings to mind images of starships leaping across galaxies, streaking lines of light, or dramatic countdowns followed by sudden silence. These images are familiar because they speak to something deeply human. We have always wanted to move faster than our surroundings allow. We invent wheels, sails, engines, and networks not just for efficiency, but because speed gives us a sense of freedom. It shortens distances, connects distant places, and makes the world feel more manageable. Faster-than-light travel is, in many ways, the ultimate expression of that impulse. It's the idea that no distance is truly out of reach, no star too far away, no future too distant to touch. Yet the universe has its own ideas about speed, and they're far less flexible than our imaginations. In everyday life, speed feels relative and negotiable. You walk faster when you're late. Cars pass each other on highways. Planes cross continents in hours instead of weeks. Each improvement feels like proof that limits are meant to be broken. But somewhere along that path of acceleration, physics places a firm hand on our shoulder and says, very politely but very clearly, that there is a line we're not supposed to cross. That line is set by light itself. Light is not just another thing that moves quickly. It occupies a special role in the universe, one that makes it different from cars, planes, sound waves, or even the fastest particles we can create in laboratories. Light doesn't simply happen to move fast. Its speed is woven into the structure of space and time. When physicists talk about the speed of light, they're not just describing how quickly photons travel from one place to another. They're describing how information, causality, and the order of events are allowed to unfold. In a very real sense, light sets the tempo of reality. This is where the idea of faster-than-light travel becomes both fascinating and unsettling. If something could move faster than light, it wouldn't just arrive sooner. It would challenge the way cause and effect work. It would blur the sequence of before and after. It would raise questions not only about where you could go, but when you might arrive. These aren't dramatic exaggerations. They are the logical consequences of how the universe appears to be built. Still, despite all of that, the question refuses to go away. Scientists continue to explore it, not because they expect an easy yes, but because understanding why something might be impossible often teaches us just as much as discovering that it's allowed, sometimes more. Faster-than-light travel sits at a crossroads where theory, experimentation and imagination meet. It's a place where physics reveals both its power and its restraint. To appreciate why this question is so persistent, it helps to step back and consider how strange speed already is, even before we push it to cosmic extremes. Speed, at its simplest, is distance over time. It sounds straightforward, almost boring. But both distance and time behave in ways that are far from intuitive once you move beyond human scales. Space can stretch, time can slow down. Measurements that seem absolute in daily life turn out to depend on motion, gravity, and perspective. When speed approaches the speed of light, these effects stop being subtle and start becoming dominant. At low speeds, everything behaves politely. You add velocities together, clocks agree with each other, rulers stay the same length. But as you move faster and faster, something odd happens. Time begins to slow down for the moving object compared to the one left behind. Distances contract along the direction of motion. Energy increases in a way that becomes increasingly difficult to manage. These are not engineering problems that can be solved with better materials or clever designs. They are features of reality itself. The speed of light is not a wall you crash into. It's more like a horizon that recedes as you approach it. No matter how much energy you pour into accelerating something with mass, it never quite reaches that ultimate speed. Instead, it gets heavier in a relativistic sense, requiring more and more energy for smaller and smaller gains in velocity. From the outside, it looks like an object asymptotically approaching the speed of light, forever getting closer, never arriving. This alone might make faster-than-light travel seem definitively impossible, and for many physicists that is exactly the conclusion. But science has a long history of discovering that rules sometimes have conditions, exceptions, or deeper explanations that change how we interpret them. The speed of light limit applies to objects moving through space, but what if space itself could move? What if the distance between 2 points could change in ways that don't require anything locally breaking the speed limit? These questions aren't loopholes in the casual sense. They arise naturally from the same theories that impose the limit in the first place. As we explore this topic together, it's important to keep in mind that science is not a list of permissions and prohibitions handed down by the universe. It's an ongoing conversation between theory and observation. Ideas are proposed, tested, refined, and sometimes discarded. Faster-than-light travel exists within that conversation not as a settled fact, but as a boundary marker, a way of probing how well we actually understand the rules we claim to know. You might notice that even asking whether faster-than-light travel is possible already assumes a particular relationship between speed, distance, and motion. It assumes that travel means moving from one location to another along a path measured against some external frame of reference. That assumption works beautifully for most of human experience, but it may not be the only way to think about movement on cosmic scales. Modern physics has taught us that space is not just an empty container. It has structure. It can expand, contract, curve, and interact with energy and matter in subtle ways. In fact, the universe itself is already doing something that looks suspiciously like faster-than-light motion, at least at very large scales. Distant galaxies are moving away from each other at speeds that exceed the speed of light, not because they are racing through space, but because space between them is expanding. This doesn't violate the cosmic speed limit because nothing is locally outrunning light. Still, it hints that our intuitive ideas about speed may not tell the whole story. This is one of the reasons faster-than-light travel remains such a compelling topic. It sits at the edge of what we know, where definitions blur and familiar concepts lose their sharpness. It invites careful thinking rather than quick conclusions, and it rewards patience. Because the answer, whatever it turns out to be, is unlikely to be simple, so for now let the question simply sit with you. Is faster than light travel actually possible? Not as a promise, not as a fantasy, but as a genuine inquiry into how the universe behaves when pushed to its limits. Speed is something we live with constantly, yet almost never pause to examine. It's woven so thoroughly into daily life that it becomes invisible, like the background hum of a refrigerator or the steady pressure of gravity holding us in place. You notice speed when you're late, when traffic slows to a crawl, or when a train rushes past with a gust of displaced air. But most of the time, speed feels flexible, negotiable, something that can be adjusted with a heavier foot on the pedal or a more efficient route on a navigation app. It gives the impression that motion is limited only by effort and ingenuity, that if we want to go faster, all we need is better technology or more energy. And yet, even in the most ordinary moments, speed is quietly bounded by limits we rarely question. These limits are so familiar that they fade into the background, shaping behaviour without ever announcing themselves. A posted speed limit on a road is an obvious example, but it's not the most interesting one. That kind of limit is imposed by society, safety and infrastructure. It can change from place to place, and people break it all the time. The more subtle limits are the ones that remain even when no one is enforcing them. Limits that emerge from physics, biology, and the structure of the world itself. Take walking, for instance. Humans have a comfortable walking speed that varies slightly from person to person, but tends to cluster around a narrow range. You can walk faster if you're in a hurry, but only up to a point. Push beyond that and walking becomes inefficient, awkward, and eventually impossible without breaking into a run. This isn't a rule someone decided. It's a consequence of how muscles work, how joints move, and how energy is transferred through the body. Your legs can only swing so fast before coordination breaks down. Your muscles can only contract and relax at certain rates. Even without thinking about it, your body respects these limits automatically. The same is true for running. Elite sprinters can reach remarkable speeds, but there's a ceiling that no amount of training has ever surpassed by more than a small margin. Human bones can withstand only so much force before risking injury. Muscles generate power within a finite range. Air resistance increases as speed increases, quietly demanding more effort for diminishing returns. No matter how motivated someone might be, no one expects a human to outrun a car on a highway. The idea feels absurd not because we've memorized numbers, but because our intuition has absorbed these limits over a lifetime of experience. Vehicles extend our natural capabilities, but they don't eliminate limits, they simply move them. Cars can travel much faster than humans on foot, but they still encounter constraints. Engines produce power within certain bounds. Tyres grip the road only up to a point before friction gives way. Curves in the road impose maximum safe speeds based on centripetal force. Even the most powerful sports car cannot turn a tight corner at highway speed without losing control. Again, these are not optional suggestions. They're consequences of how mass, force and motion interact. Airplanes push the envelope further. They move faster than cars, faster than trains, lifting themselves off the ground entirely. To many people, flight already feels like cheating the ordinary rules of motion. But planes too have speed limits that pilots take very seriously. Fly too slowly, and the wings no longer generate enough lift, leading to a stall. Fly too fast and the structure of the aircraft can be stressed beyond its design limits, or airflow can behave in dangerous ways. Commercial jets cruise within a narrow window of speeds, where physics, efficiency and safety align. They don't simply go as fast as possible, because faster is rarely better once all the constraints are considered. Even sound has a speed limit that shapes experience in ways we've come to take for granted. You see lightning before you hear thunder because sound travels much more slowly than light. Supersonic aircraft must contend with shock waves and sonic booms, not as dramatic special effects, but as unavoidable consequences of compressing air faster than it can naturally move out of the way. Engineers don't ignore these effects. They work around them, designing shapes and materials that manage shock waves rather than pretending they don't exist. What's striking about all these examples is how uncontroversial they feel. No one argues that walking faster than a certain speed should be possible if we just try harder. No one expects cars to corner infinitely well, or airplanes to ignore aerodynamics. We accept these limits because they're visible, tangible, and repeatedly confirmed by experience. They form a quiet framework that shapes how we move through the world. This everyday familiarity with limits is important, because it sets the stage for understanding why the speed of light is different, and why it resists being treated as just another barrier waiting to be broken. In daily life, speed limits usually feel external. They arise from friction, structural strength, energy supply, or safety concerns. They can often be shifted incrementally. Better materials allow higher speeds, smoother roads reduce friction, more powerful engines overcome resistance. Progress feels like a steady march forward, pushing boundaries outward year after year. The cosmic speed limit does not behave this way. It doesn't yield gradually to better engineering, because it isn't imposed by materials or design. It's woven into the relationship between space and time themselves. But before reaching that conclusion, it helps to notice how even familiar limits already hint at something deeper. Consider reaction time. No matter how alert you are, there is a delay between seeing something and responding to it. Nerve signals take time to travel. Muscles take time to contract. This delay is small, but it's real, and it sets a limit on how quickly you can respond to changes in your environment. Athletes train to reduce reaction time, but no one reaches zero. The limit isn't psychological, it's physical. Information must move through biological systems, and it cannot do so instantaneously. Now think about communication. You send a text message and expect it to arrive almost immediately. Most of the time it does. But that apparent immediacy depends on a vast infrastructure of signals moving through cables, fiber optics, and wireless networks. Those signals are fast, but they're not instantaneous. Over long distances, delays become noticeable. Anyone who has spoken to someone on the other side of the planet via video call has experienced the slight lag, the tiny pause that interrupts conversational rhythm. That pause exists because information takes time to travel, even when moving at a significant fraction of the speed of light. These small delays are everyday reminders that information itself is not exempt from speed limits. Causes precede effects. Messages take time to arrive. Coordination requires anticipation because responses cannot be instantaneous. The world functions smoothly precisely because these delays are predictable and consistent. If information could arrive before it was sent, or if responses could precede stimuli, everyday life would be deeply confusing. Even perception is shaped by speed limits. When you look at something, you are seeing it as it was a fraction of a second ago, because light takes time to reach your eyes. For nearby objects, the delay is negligible, but it grows with distance. When you look at the sun, you see it as it was about 8 minutes ago. This isn't a poetic statement, it's a literal one. The light arriving now left the sun minutes earlier. If something dramatic happened there in this instant, you wouldn't know right away. The universe does not provide live updates without delay. All of this happens so seamlessly that it rarely registers as remarkable. We adapt. Our brains fill in gaps, smooth over delays, and create the illusion of immediacy. But beneath that illusion is a strict ordering of events enforced by finite speeds. Information flows, but it flows at a pace set by nature. What makes the speed of light particularly interesting is that it seems to be the ultimate version of this principle. It's not just that light moves very fast, it's that nothing with mass has ever been observed to move faster, and nothing carrying information has been shown to outrun it. This universality is what elevates it from a practical limit to a fundamental one. In everyday contexts, when we encounter a limit, we instinctively ask what's causing it. Is it friction, Is it inefficiency? Is it a design flaw? Usually the answer is yes, and improvement is possible. But the more we examine the speed of light, the less it behaves like an obstacle that can be removed. Instead, it acts like a rule that defines how motion, energy, and time relate to one another. To appreciate how unusual this is, imagine if walking speed were universal. Imagine if no matter what species you were, no matter your size or environment, there was a maximum walking speed that could never be exceeded. That would feel less like a biological constraint and more like a property of space itself. The speed of light is closer to that kind of limit than any we encounter in daily life. Yet, because we don't move anywhere near light speed, it's easy to underestimate how deeply it already shapes experience. Every electrical signal in your body, every radio transmission, every reflection you see depends on it. The world you perceive is stitched together by light and other signals moving at finite speeds, creating a coherent sequence of events that your mind interprets as the present. This sequence is what gives rise to the sense of now. Not a universal now, but a local one, defined by what signals have had time to reach you. Your present is bounded by light cones, regions of space-time from which information can arrive within a given time. You don't need to know this term to live within its constraints. You already do, effortlessly. The reason this matters for faster-than-light travel is that any proposal to exceed this speed isn't just about going faster. It's about rearranging the order of events. It's about allowing effects to appear without clear causes, or causes to arrive after their effects. Even at everyday scales, such disruptions would be deeply unsettling. At cosmic scales, they challenge the logical structure of physical law. Still, the fact that these implications are profound doesn't automatically make faster-than-light travel impossible. Nature has surprised us before. What it does mean is that any such possibility would have to contend not just with engineering challenges, but with the way reality maintains consistency. As we continue, it helps to carry this sense of quiet limitation with us. The world is not infinitely flexible. It allows motion, change, and connection, but within patterns that are remarkably stable. These patterns show up when you walk, when you drive, when you communicate, and when you simply look around. They are so reliable that they become invisible. Understanding faster-than-light travel begins not with exotic equations or distant stars, but with noticing how much of everyday life already depends on speed limits that no one voted for and no one enforces, yet everyone obeys. From here, the question becomes more focused. If there is an ultimate speed limit underlying all others, how did we come to recognize it, and why does light, of all things, occupy that role? Light occupies a strange position in our understanding of the world. It is everywhere, constantly arriving, constantly moving, yet so familiar that it rarely feels mysterious. You wake up because light filters through a window. You recognize faces because light reflects off them. You read words, notice colors, and orient yourself in space because light carries information to your eyes. It feels passive, almost gentle, like something that simply reveals what is already there. But beneath that calm familiarity lies one of the most active roles anything plays in the universe. Light is not just illumination. It is nature's fastest messenger. Long before anyone measured its speed, people understood that light was special. Ancient thinkers debated whether vision happened because something left the eye and touched objects, or because something travelled from objects into the eye. Even without precise experiments, there was an intuition that light was doing the travelling. What no one could tell at the time was how fast that journey took, or whether it took time at all. For centuries, many assumed that light moved instantaneously. After all, when you open your eyes, the world appears all at once. There is no obvious delay, no sense of waiting for photons to arrive. The first cracks in that assumption came not from laboratories, but from astronomy. When observers studied the motion of distant moons and planets, they noticed something odd. Certain events appeared slightly earlier or later depending on Earth's position in its orbit. These discrepancies were small but persistent, The most elegant explanation was that light did not arrive instantly. It took time to cross space, and when distances changed, so did the timing of what was seen. Light, it turned out, had a speed, and that speed was finite. Once that idea took hold, curiosity accelerated quickly. If light had a speed, how fast was it? Measuring it was not easy. Light moves far faster than any everyday object, covering vast distances in fractions of a second. Early experiments relied on rotating mirrors, distant reflections, and increasingly clever setups designed to stretch tiny intervals of time into something measurable. With each refinement, the same conclusion emerged. Light was extraordinarily fast, but not infinite. As measurements improved, something even more intriguing became clear. The speed of light did not seem to depend on how it was produced. Whether light came from a candle, the sun, or an electrical spark, its speed in empty space was the same. This was deeply counterintuitive. In everyday experience, speeds add and subtract. Throw a ball from a moving train, and its speed depends on both the throw and the train. Light refused to behave this way. No matter how fast the source moved, light still raced away at the same speed. This consistency transformed light from a simple phenomenon into a cornerstone of physics. It suggested that light was not just another thing moving through space, but something more fundamental, tied to the structure of space and time themselves. Instead of asking how fast light travels, physicists began to ask why it travels at that speed, and why nothing else seems able to outrun it. To understand why light holds this role, it helps to consider what light actually is. At a basic level, light is an electromagnetic wave, a coordinated oscillation of electric and magnetic fields. These fields do not need a medium to propagate. They sustain each other, moving through empty space without friction or resistance. This already sets light apart from sound, which requires air, or water waves, which require water. Light travels just as comfortably through the vacuum between stars as it does through glass or air, though its speed changes slightly in materials. Because light is massless, it does not experience inertia in the way objects with mass do. You do not need to push light to keep it moving. Once it exists, it moves, and it does so at its characteristic speed. This is not because it is trying to go fast, but because there is no slower option available to it. In a sense, light does not accelerate up to its speed. It simply is that speed. This idea can feel slippery, especially because acceleration and deceleration are so deeply ingrained in human intuition. We expect motion to involve effort and resistance. Light sidesteps that entire framework. It is created and immediately moves at its full speed, without warming up, without ramping up energy, without any transitional phase. That alone makes it a natural candidate for the role of fastest messenger. But speed alone does not explain why light defines the ultimate limit. After all, if something else were massless, couldn't it move faster? This is where the story becomes more subtle. In the equations that describe electromagnetism, the speed of light appears not as a variable, but as a constant determined by fundamental properties of space itself. It emerges from the relationship between electric and magnetic fields, encoded in values that describe how space responds to them. Change those values, and you would change the speed of a light, along with the nature of reality as we know it. Over time, physicists realized that the speed of light was doing double duty. It was not only the speed at which light waves propagate, it was also the speed at which any influence, any signal, any causal connection could travel. Light was simply the most obvious carrier, but the limit applied more broadly. Gravity waves, changes in electromagnetic fields, and other interactions all respect the same maximum speed. Light just happens to saturate it. This is why light is often described as the universe's speed limit sign. Not because it restricts light, but because light reveals the restriction for everything else. Nothing that carries information can exceed it. Nothing that has mass can reach it. Everything else moves more slowly, whether by a tiny margin or an enormous one. In practical terms, this makes light the backbone of communication. When you look at something, light carries information about its shape, colour, and position. When telescopes peer into deep space, they are not seeing distant objects as they are now, but as they were when their light began its journey. Light becomes a time capsule, preserving moments from the past and delivering them to the present. This messenger role has profound consequences. It means the universe does not exist as a single, synchronized moment. Different regions experience different nows, depending on how far apart they are and how fast information can travel between them. Light defines the boundaries of what can influence what and when. Events outside your light horizon may as well not exist yet, because no signal from them has had time to reach you. Even within everyday distances, this principle quietly shapes reality. When you watch someone across a room, the delay is minuscule, but it is still there. When you communicate across continents, the delay becomes noticeable. When signals cross planetary distances, delays stretch into minutes or hours. Each step outward reinforces the same lesson. Information takes time, and light sets the pace. This role as messenger also explains why light is so central to discussions of faster-than-light travel. If you could move faster than light, you could arrive somewhere before light from your departure point arrived there. That means you could, in principle, influence events before information about your actions had time to propagate. Cause and effect would no longer have a consistent order for all observers. This is not a philosophical inconvenience. It is a structural problem. Physics relies on consistent causal relationships. Equations assume that inputs lead to outputs in an orderly way. Light speed provides the scaffolding that keeps those relationships stable across space and time. Remove or bypass that scaffolding, and the structure begins to wobble. Yet, the idea that light is the fastest messenger does not mean it is perfect or all-powerful. Light interacts with matter. It can be absorbed, scattered, or redirected. In dense materials, it slows down, not because it is violating its own rules, but because it is constantly interacting with atoms, being absorbed and re-emitted in tiny steps. Even then, the underlying limit remains. The interactions take time, and the overall effect is slower propagation. Interestingly, this slowing of light in materials has sometimes led to confusion. Experiments have demonstrated situations where light pulses appear to travel faster than the speed of light in vacuum, or even emerge before they enter a medium. These effects, while fascinating, do not actually transmit information faster than light. They arise from the reshaping of wave packets and the subtleties of how signals are defined. When examined carefully, the causal structure remains intact. Light still guards the boundary. The more deeply scientists have probed light's behaviour, the more robust its role as ultimate messenger has become. Quantum mechanics revealed that light also behaves as particles, photons, carrying discrete packets of energy. Even in this particle-like description, photons remain massless and travel at the same invariant speed. Whether treated as waves or particles, light refuses to slow down in empty space. At the same time, quantum theory adds layers of nuance. Photons can be created and destroyed. They can become entangled. They can exist in superpositions. Yet none of these features allow them to outrun their own speed limit. The message remains consistent. However strange the underlying behaviour becomes, the pace at which information travels does not change. This consistency has led physicists to elevate the speed of light from a measured quantity to a defining constant. Today, the meter itself is defined in terms of how far light travels in a specific fraction of a second. Rather than measuring light's speed, we define distances by it. This is a subtle but profound shift. It reflects a deep confidence that light's speed is not just stable, but foundational. Seen this way, light is not merely fast, it is the standard against which motion is judged. It provides the ruler and the clock for the universe. When objects move close to its speed, time and space adjust around them. Not because light is being accommodated, but because reality is structured to preserve its role. All of this makes light an unlikely candidate to be overtaken, and yet the human imagination persists. If light is the fastest messenger, could there be a way to send messages without relying on messengers at all? Could space itself be rearranged so the distances shrink, allowing arrival without traditional travel? These questions do not come from ignorance of light's role, but from engaging with it deeply. Before those ideas can be explored, though, it's important to sit with what it means for light to be the universe's courier. Every observation, every measurement, every piece of knowledge we have about the cosmos arrives carried by light or signals bound by the same limit. We're always looking into the past, even when the past is only nanoseconds old. Our sense of immediacy is an illusion created by the sheer speed of light compared to human scales. As the focus gradually shifts from light itself to the rules that elevate it to this status, the question becomes sharper. If light defines the maximum speed for information and influence, what happens when we try to imagine moving faster than that? Once light is recognized as nature's fastest messenger, an obvious question follows almost automatically. Why should that be the case at all? Why should there be a maximum speed written into the universe? And why should nothing be allowed to outrun it? At first glance, the idea feels oddly restrictive, almost arbitrary, as though reality has imposed a rule simply to make things difficult. In everyday life, limits usually exist for practical reasons. Materials break, engines overheat, bodies get tired. These limits feel negotiable, something clever engineering might eventually overcome, but the limit imposed by light behaves differently. It does not weaken under pressure. It does not shift when technology improves. Instead, it reveals itself more clearly the closer one tries to approach it. To understand why nothing is supposed to outrun light, it helps to let go of the idea that speed is just about covering distance quickly. In classical thinking, speed is distance divided by time, and both distance and time are assumed to be fixed, universal quantities. A meter is a meter everywhere. A second is a second everywhere. Motion happens within this rigid stage, and velocities simply add together. Within that framework, there is no obvious reason for a universal speed limit. You can always imagine going a bit faster, given enough energy. The difficulty is that this framework turns out not to describe reality accurately once speeds become extreme. Experiments involving light-forced physicists to confront a contradiction. Measurements showed that the speed of light appeared the same for all observers, regardless of how fast those observers were moving. This result was not a minor inconvenience. It struck at the heart of how motion itself was understood. If two people are moving relative to each other and both measure the same light speed, then something else must be changing to compensate. Distance and time can no longer remain absolute. The resolution to this puzzle led to a profound shift in perspective. Space and time were no longer separate, rigid backgrounds. They became intertwined, flexible, and dependent on motion. When objects move faster, time slows down for them relative to others. Lengths contract along the direction of motion. These effects are not optical illusions or measurement errors. They are real changes in how intervals of space and time are experienced. Within this framework, the speed of light emerges not as a barrier enforced by resistance, but as a structural feature of space-time itself. It is the speed at which cause and effect propagate. The speed at which changes can influence distant regions. Nothing is forbidden from going faster in the sense of being blocked by an external force. Instead, the geometry of space-time adjusts in such a way that reaching or exceeding that speed becomes impossible for anything with mass. One way to see this is to consider energy. As an object accelerates, its kinetic energy increases. At low speeds, this increase behaves in a familiar way. Double the speed, and the energy increases by a predictable amount. But as speed approaches the speed of light, this relationship changes dramatically. Each additional increment of speed requires disproportionately more energy. Near the light speed limit, the required energy grows without bound. No matter how much energy you supply, you never quite reach the limit. The object responds by increasing its relativistic mass and slowing its internal clocks instead. This is not an engineering challenge that awaits a clever workaround. It is a mathematical consequence of how energy, momentum, space, and time relate. The equations do not contain a term that says stop here. They simply imply that the closer you get, the harder it becomes until the required energy diverges toward infinity. In practical terms, infinity is an impassable wall. This explains why massive particles in accelerators, despite being pushed with enormous energies, always fall short of light speed. They can get extremely close, differing by a tiny fraction of a percent, but never reach or exceed it. Light, being massless, does not face this problem. It does not need to be accelerated. It exists already at the limiting speed. Another way to understand the limit is through causality. The universe appears to be organized in such a way that causes precede effects. This ordering is not just a psychological preference. It is embedded in physical law. Signals propagate outward from events, influencing other events in a consistent sequence. The speed of light defines the maximum speed at which these influences can travel. If something could outrun light, this ordering would break down. For some observers, an effect could be seen before its cause. Messages could arrive before they were sent. This is not merely strange, it undermines the logical consistency of physical descriptions. Laws of physics rely on being able to predict outcomes based on initial conditions. If those outcomes could influence the conditions that created them, prediction loses its footing. Importantly, this issue does not depend on human perception or measurement limitations. It arises directly from how different observers moving, relative to each other, relate time and space. When speeds exceed the speed of light, the equations that transform coordinates between observers begin to produce negative time intervals. Events that are separated in one order for one observer appear reversed for another. The universe would no longer agree on what happened first. The speed of light prevents this disagreement from becoming physically meaningful. It acts as a boundary separating events that can influence each other from those that cannot. Inside that boundary, causality is preserved. Outside it, events are disconnected in a way that prevents paradoxes from manifesting. This structure is sometimes visualized using cones in spacetime diagrams, but even without diagrams, the idea is straightforward. There are limits to what can affect what, and light defines those limits. It is tempting to think of this as an inconvenience imposed by theory, but in practice it is what makes a stable universe possible. Imagine a world where influences could propagate instantaneously or faster than light. Interactions would not have a clear order. Systems could respond to changes before they occurred. Feedback loops could arise that have no consistent resolution. The universe would be less like a sequence of events and more like a tangled knot of contradictions. This does not mean that reality is fragile or finely tuned in a delicate way. On the contrary, the speed limit seems to be deeply woven into its fabric. The same constant appears in electromagnetism, in relativity, and in the structure of space-time itself. It is not an add-on, it is foundational. Another point that often causes confusion is the distinction between speed through space and changes to space itself. Objects are constrained in how fast they can move through space-time, but space-time itself can change in ways that do not involve motion in the usual sense. This distinction is crucial, because it explains why certain phenomena, like the expansion of the universe, do not violate the light speed limit even when distances between objects grow faster than light could traverse. This nuance sometimes leads to the impression that the light speed limit is more flexible than it really is. But flexibility here applies to geometry, not to local motion or information transfer. Locally, in any small region of space-time, the same rules apply. No signal outruns light. No massive object reaches its speed. From this perspective, the phrase, "nothing is supposed to outrun light," is slightly misleading. It suggests an imposed rule, as though the universe could have chosen otherwise. A more accurate way to phrase it is that light defines the structure within which motion and causality exist. To outrun light would not be to break a rule, but to step outside the framework that gives the rule meaning in the first place. This is why proposals for faster-than-light travel often avoid direct acceleration. They look instead for ways to alter distances, to fold space, or to exploit exotic features of space-time geometry. These ideas attempt to respect the local speed limit while still achieving effective faster-than-light outcomes. Whether they succeed is another question entirely, but their motivation comes directly from the realization that outrunning light locally leads to deep contradictions. It's also worth noting that the light speed limit is not something we feel emotionally constrained by in daily life. We're so far below it that its effects are imperceptible. Time dilation, length contraction, and energy divergence only become noticeable at speeds far beyond anything humans experience directly. This distance makes the limit feel abstract, theoretical, and perhaps negotiable. But abstraction does not imply weakness. Gravity felt abstract before it was understood. So did electricity. Their effects were always there, shaping reality long before they were named. As understanding deepened, the light speed limit transformed from a curiosity into a guiding principle. It explained why information has horizons. It clarified why simultaneity is relative. It unified space and time into a single entity, whose geometry responds to motion and energy. Far from being a minor detail, it became one of the pillars on which modern physics rests. Still, none of this extinguishes curiosity. Knowing why something appears forbidden often invites the question of whether the prohibition is absolute or contextual. Is the speed of light an unbreakable wall, or is it a boundary that can be approached from unexpected angles? Can effective faster-than-light behavior emerge without violating local causality? When people talk about limits in physics, they often imagine barriers, something you crash into or bounce off, a wall, a ceiling, a hard stop. But the limit introduced by Einstein does not behave like that at all. It's quieter, more subtle, and in many ways more unsettling, because you never actually reach it. You just find that the universe responds differently the closer you get. This is why it's often helpful to think of Einstein's contribution not as a prohibition, but as a kind of cosmic speed bump, one that gently but relentlessly changes how motion itself works, as velocities climb higher and higher. Before Einstein, speed felt simple. You could always ask, how fast is something moving, and expect a straightforward answer. Motion was measured against an invisible, unmoving backdrop. Space was space. Time was time. They existed independently of what was happening within them. If two observers disagreed about a speed, it was assumed one of them was mistaken, or measuring incorrectly. The idea that both could be right at the same time did not make sense. Einstein did not begin by trying to overthrow this picture. He was responding to a very specific problem. Experiments had shown that the speed of a light appeared to be the same for all observers, regardless of how fast they were moving. This was not a philosophical claim. It was a measured result, and it stubbornly refused to fit into the old framework. If velocities added the way everyone assumed, then observers moving toward or away from a light source should measure different speeds. They didn't. Rather than trying to explain this away, Einstein took it seriously. He made a bold move that, in hindsight, seems almost inevitable, but at the time was deeply counterintuitive. He proposed that the speed of light is the same for all observers, and that the laws of physics are the same for all observers moving at constant speeds. If those statements are true, then space and time themselves must adjust to make them true. This is where the speed bump appears. Instead of speed increasing indefinitely as more energy is added, the universe begins to compensate. Time slows down for the moving object. Lengths contract along the direction of motion. Simultaneity breaks apart. meaning events that seem to happen at the same time for one observer may not for another. None of this happens abruptly. There is no moment where the universe flashes a warning light. The effects begin subtly and grow stronger as speed increases. At everyday speeds, the changes are so small they are completely negligible. You do not notice your clock ticking more slowly because you are walking down the street. Your ruler does not shrink when you drive to the store. The speed bump is there, but it is so gentle at low speeds that it might as well not exist. This is why classical physics works so well in ordinary circumstances. It is not wrong so much as incomplete. As speed increases, however, the bump becomes more pronounced. Clocks moving at high speed tick more slowly compared to clocks at rest. This is not a metaphor. It is not about perception or mechanical failure. Time itself, as experienced by the moving system, passes more slowly. Lengths along the direction of motion shorten. From the perspective of the moving object, the outside world appears distorted as well. Each observer sees the other as the one experiencing these effects. This mutuality is important. There is no privileged frame of reference, no absolute state of rest. Motion is always relative, and the laws of physics do not single out a preferred observer. The speed bump applies universally, adjusting reality locally for each observer in a way that preserves the consistency of physical law. The closer an object's speed gets to the speed of light, the stronger these effects become. Time dilation increases, length contraction becomes more extreme. Energy requirements grow rapidly. From the perspective of an external observer, the moving object appears to approach the speed of light more and more slowly, never quite reaching it. From the perspective of the moving object, its own experience remains normal. Its clocks tick regularly. Its rulers behave as expected. What changes is its relationship to the rest of the universe. This is why the speed of light is not just fast, it is unattainable for anything with mass. To reach it would require time dilation to become infinite and lengths to contract to zero. The equations do not allow for a smooth crossing of this boundary. The speed bump becomes infinitely steep. Einstein did not introduce this behavior as a patch or a workaround. It emerges naturally from the structure of spacetime once the constancy of the speed of light is accepted. Space and time are no longer separate entities. They form a single four-dimensional fabric, spacetime, within which motion takes place. Speed is not just movement through space. It is movement through space-time, and the geometry of that space-time responds to motion. One way to think about this is to imagine that everything is always moving through space-time at the same combined speed. Objects at rest in space move fully through time. Objects moving through space divert some of that motion away from time. As more motion goes into space, less remains for time. This is not a literal picture, but it captures the trade-off encoded in the equations. You cannot increase spatial speed without affecting temporal flow. Light occupies a special position in this framework. It moves entirely through space and not through time, at least from its own perspective. This is a strange statement, because it is not meaningful to talk about a photon's perspective in the usual sense. But mathematically, light travels along paths for which time does not pass. This is another way of seeing why it cannot be slowed down or sped up. It already sits at the extreme edge of what spacetime allows. The speed bump introduced by Einstein also reshapes how energy behaves. As an object accelerates, its energy increases, but not linearly. Each additional increase in speed requires more energy than the last. Near the speed of light, the energy required to gain even a tiny increment becomes enormous. This is why particle accelerators, despite reaching incredible energies, still cannot push massive particles past light speed. They run headlong into the same geometric constraint. It is tempting to imagine that some new technology might eventually overcome this, but the limitation is not technological. It is structural. It arises from the way spacetime relates energy, momentum, and motion. To bypass it would require altering the geometry itself, not merely applying more force. Einstein's speed bump also clarifies why faster-than-light travel is not just about going faster. It is about changing the relationship between observers, events, and causality. At speeds below light speed, the order of cause and effect remains consistent across observers. Disagreements about simultaneity do not lead to contradictions, because influences still propagate within well-defined limits. Once speeds exceed the speed of light, this consistency breaks down. The equations allow events to swap temporal order depending on the observer. A signal sent from one place could be received before it was sent, at least from certain perspectives. This is not a speculative add-on. It falls directly out of the mathematics of space-time transformations. The speed bump prevents this regime from being accessible to objects and signals. It keeps all physical processes within a domain where causality remains intact. In this sense, Einstein's contribution is not merely restrictive, it is protective. It ensures that the universe has a consistent narrative structure, where events unfold in an order that can be agreed upon locally. What makes this especially interesting is that Einstein did not set out to enforce causality as a philosophical principle. He followed the evidence. The preservation of causal order emerged as a consequence of taking the speed of light seriously. This is often how physics advances. Deep principles are not imposed from above. They arise from insisting that observations be explained without contradiction. Another subtlety of Einstein's speed bump is that it applies only to local motion through space-time. It does not prohibit all forms of effective faster-than-light behavior. Distances can change, space can expand, geometries can be curved. These possibilities exist within the same framework that enforces the local speed limit. This is why discussions of warp drives and wormholes arise naturally once general relativity enters the picture. They are attempts to respect the speed bump while still achieving dramatic outcomes. At this stage, though, it is important not to jump too far ahead. Einstein's original insight concerned motion at constant speeds and the structure of space-time itself. It did not require exotic matter or speculative engineering. It required only the willingness to accept that time and space are not absolute. That acceptance comes with consequences that ripple outward into nearly every corner of physics. It changes how we think about clocks and rulers. It changes how we synchronize events. It changes how energy and momentum behave. And it changes what we mean when we say that something is possible or impossible. One of the most counterintuitive aspects of this picture is that nothing feels wrong locally. From inside a fast-moving system, everything behaves normally. Physics proceeds as usual, clocks tick, processes unfold. There is no sensation of approaching a limit. The speed bump is experienced only in comparisons between observers. It is relational, not absolute. This is part of why the speed of light limit can feel abstract and negotiable. We never feel it directly. We infer it through measurements and calculations, but its effects are not hypothetical. They are confirmed every day in technologies that rely on precise timing. Satellite navigation systems, for example, must account for time dilation due to both speed and gravity. Without Einstein's corrections, their errors would accumulate rapidly. These practical confirmations underscore that the speed bump is not a mathematical curiosity. It is an active feature of the world. It shapes how systems behave when precision matters. It quietly enforces consistency across vast distances and extreme conditions. As attention begins to turn toward the possibility of faster-than-light travel, Einstein's speed bump looms large. It is not a simple obstacle that can be ignored or bulldozed. It is a reshaping of the terrain itself. Any proposal that hopes to move beyond it must grapple with the geometry of space-time, not just the mechanics of motion. This does not mean that the conversation ends here. On the contrary, it becomes more interesting. Once speed is understood as something woven into space and time, new questions emerge. If space-time can respond to motion, can it be manipulated? If geometry enforces limits, can geometry be altered? When people first hear that time slows down at high speeds, the reaction is often disbelief mixed with a kind of casual curiosity. It sounds like a clever phrase, something meant to gesture at complexity without demanding too much attention. But time slowing down is not a metaphor, and it is not a trick of perception. It is a literal description of how the universe behaves when motion becomes extreme. What makes this idea difficult to absorb is not that it is complicated, but that it clashes so directly with how time and space feel in everyday life. In ordinary experience, time seems stubbornly uniform. A second passes, then another, all marching forward at the same pace. Space feels equally stable. A meter today is the same length as a meter tomorrow. You can leave a room, come back later, and trust that its dimensions have not quietly rearranged themselves while you were gone. This sense of stability is so deeply ingrained that it feels like a feature of reality itself rather than a convenient approximation. Einstein's work revealed that this stability is conditional. It holds only when speeds are low and gravitational fields are weak. Under those circumstances, space and time behave well enough to be treated as fixed backgrounds. But once speeds increase, that simplicity dissolves. Space and time stop acting like rigid containers and begin to behave like flexible participants. To understand what really slows down, it helps to separate intuition from description. When physicists say that time slows down for a moving object, they do not mean that its internal processes become faulty or delayed. Nothing inside the object malfunctions. Chemical reactions proceed normally. Biological processes unfold as usual. From the perspective of the moving system, everything feels ordinary. Clocks tick once per second. Hearts beat at their normal rhythm. There is no sensation of dragging or delay. The slowing of time becomes apparent only when comparisons are made between systems moving relative to one another. Take two identical clocks. Keep one at rest relative to some reference point, and send the other on a high-speed journey before bringing it back. When they are reunited, the moving clock will show less elapsed time. This is not because it was damaged or poorly calibrated. It is because less time actually passed along its path through space-time. This idea introduces a subtle but important shift. Time is no longer a universal river flowing equally for all observers. It becomes something that depends on the path taken through space-time. Different paths accumulate different amounts of time, just as different routes between two cities can have different lengths. Space undergoes a similar transformation. Length contraction is often described as objects shrinking along the direction of motion. Again, this is not a physical squeezing or deformation experienced by the object itself. From its own perspective, its dimensions remain unchanged. The contraction appears only when measured by an observer relative to whom the object is moving. These two effects, time dilation and length contraction, are not independent quirks. They are two sides of the same underlying change. Space and time are linked. Altering one alters the other. Together, they ensure that the speed of light remains the same for all observers, preserving the consistency of physical law. A useful way to think about this is to imagine space-time as a single entity with a fixed geometry. Motion through this geometry involves trade-offs. If more of your motion goes into space, less goes into time. If more goes into time, less goes into space. This is not a choice made by the object. It is simply how the geometry responds. From this perspective, asking what really slows down becomes more precise. It is not that time itself is an independent substance being stretched or compressed. It is that the interval of time measured along a particular path through space-time differs from that measured along another. The difference emerges naturally from the geometry. This geometric view also clarifies why there is no privileged observer. Each observer carries their own measure of time and space, defined locally by their motion. There is no universal clock ticking in the background against which all others can be compared. What exists instead is a consistent set of rules that relate different observers' measurements to one another. These rules have been tested repeatedly. High-speed particles live longer than their slower counterparts because their internal clocks run more slowly relative to the laboratory frame. Precision clocks flown on aircraft or placed in orbit tick at different rates than identical clocks on the ground. These are not theoretical predictions awaiting confirmation. They are observed facts that must be accounted for in practical systems. One of the reasons this still feels surprising is that human intuition evolved in a regime where these effects are vanishingly small. At walking or driving speeds, time dilation and length contraction are so tiny that they might as well not exist. The universe is kind enough, in everyday circumstances, to behave as though space and time are absolute. As speeds increase, however, the approximations break down. The changes do not happen suddenly. There is no threshold where time abruptly starts slowing down. Instead, the effect increases smoothly with speed. At first it is imperceptible, then it becomes measurable, eventually it dominates. What makes the speed of light special in this context is that it represents the point where these trade-offs reach their extreme. As an object approaches light speed, time dilation grows without bound. From the perspective of an external observer, the moving clock ticks more and more slowly. Length contraction along the direction of motion becomes more pronounced. Energy requirements skyrocket. At the speed of light itself, the equations indicate that time dilation would be infinite. Time along that path would not pass at all. This is why it is often said that light does not experience time. This is not a poetic statement, but a mathematical one. The space-time interval along a light-like path is zero. There is no elapsed proper time. This result can feel unsettling, because it challenges the assumption that time is something that must always pass. Light shows that this assumption is false. Time passes for systems with mass, following paths that are time-like. For light, which follows null paths, the concept of time passing along its trajectory simply does not apply. This distinction also explains why nothing with mass can reach or exceed the speed of light. To do so would require following a path through space-time that is not time-like. The geometry does not allow massive objects to transition smoothly onto null or space-like paths. The required energy diverges before that happens. Seen this way, the question of what slows down becomes almost beside the point. It is not that time slows down because something is moving fast. It is that the geometry of space-time assigns different time intervals to different paths. Speed is not the cause of time dilation, so much as a symptom of how motion through space-time is distributed. This reframing helps avoid a common misunderstanding. Time dilation is sometimes imagined as a physical process that acts on clocks, like friction acting on gears. But clocks are simply devices that count regular processes. They reveal time dilation because the processes themselves unfold differently along different paths. The clock is not being acted upon. It is faithfully recording what happens. The same applies to biological aging. When astronauts age more slowly than people on Earth, it is not because their bodies are malfunctioning. It is because fewer proper seconds pass along their world lines. Their chemistry, metabolism, and cellular processes unfold normally within their own frame. Space, too, behaves in a way that resists everyday intuition. Length contraction does not mean that objects are compressed or damaged. It means that different observers disagree about the distance between 2 points when those points are in relative motion. Distance becomes a relational quantity rather than an absolute one. This relational nature of space and time is what makes faster-than-light travel so problematic. If space and time were independent and absolute, one might imagine exceeding a speed limit by sheer effort. But when they are intertwined, pushing on one dimension reshapes the other. You cannot increase speed indefinitely without altering the temporal structure that gives speed meaning. It is also important to recognize that time dilation and length contraction are not arbitrary adjustments made to preserve the speed of light. They arise naturally from a deeper symmetry in the laws of physics. The equations that describe electromagnetism, mechanics, and eventually gravity all respect this symmetry. The constancy of the speed of light is not a bolt-on constraint. It is a reflection of this underlying structure. This structure has a name, space-time symmetry, but the name is less important than the consequence. The universe does not privilege one state of uniform motion over another. The laws of physics look the same to all observers moving at constant speeds. This principle, combined with the observed behavior of light, leaves only one consistent option. Space and time must adjust. Once this adjustment is accepted, many things fall into place. The impossibility of faster-than-light motion for massive objects becomes a direct consequence rather than a mysterious rule. Causality remains intact because signals cannot outrun light. The ordering of events remains consistent within local regions of space-time. At the same time, this framework opens the door to new questions. If time and space are flexible, can they be shaped or manipulated? If geometry enforces limits, can geometry itself be engineered? These questions do not arise from rejecting Einstein's insights, but from taking them seriously. Before those ideas can be explored, though, it is important to remain grounded in what the theory actually says. Time does not slow down universally. Space does not shrink universally. These effects are relative, dependent on motion and perspective. They do not represent malfunctions or distortions of reality. They are reality behaving as it always does, revealed only under extreme conditions. In everyday life, the cosmic speed bump introduced earlier is so gentle that it goes unnoticed. Time feels steady. Space feels fixed. The universe cooperates with human intuition. But at higher speeds, that cooperation fades. The deeper structure becomes visible, and with it comes a new understanding of what motion really means. This understanding is essential for any serious discussion of faster-than-light travel. It clarifies what kinds of changes are allowed and which ones threaten the consistency of physical law. It shows that speed limits are not imposed from outside but emerge from the way space and time are woven together. With this in mind, attention naturally begins to drift toward a question that has intrigued physicists for decades. If moving faster through space slows down time, and if light already sits at the extreme edge of that relationship, are there other ways to achieve dramatic effects without directly accelerating to forbidden speeds? Once the speed of light is understood not as a simple barrier, but as a structural feature of space-time, it becomes tempting to assume the conversation is over. If nothing with mass can reach or exceed that speed, if time and space reshape themselves to prevent it, then faster-than-light travel sounds decisively ruled out. And yet, physics has a habit of becoming more interesting precisely at the point where something appears settled. The deeper scientists have explored the foundations of space-time, the more they've uncovered situations that don't quite fit into tidy categories of possible and impossible. These are not loopholes in the sense of broken rules or mistakes. They are strange corners of theory where the rules interact in unexpected ways. The word loophole can be misleading here. It suggests trickery or shortcuts, as though nature can be fooled into allowing something it clearly doesn't want. What physicists actually mean are scenarios where the speed of light limit is respected locally, yet the overall outcome looks suspiciously like something travelling faster than light. Nothing outruns light in its immediate neighbourhood. No signal locally exceeds the limit, and yet the separation between two distant points can shrink or be bypassed in ways that feel almost dishonest at first glance. One of the earliest hints that such behaviour might be possible comes from cosmology rather than engineering. When astronomers observe distant galaxies, they find that many of them are receding from us at enormous speeds. Some are moving away so fast that, when measured using standard cosmological distances, their recession speed exceeds the speed of light. This sounds like a direct violation, until the details are examined more carefully. What's happening in these cases is not motion through space, but expansion of space itself. The galaxy is not racing away like rockets. They are being carried along as the fabric of space-time stretches between us and them. Locally, in the region around each galaxy, the laws of physics behave normally. No object outruns light nearby. But globally, the distance between far apart regions increases faster than light could traverse it. This distinction is subtle but crucial. The speed limit applies to objects and signals moving through space-time, not to changes in the geometry of spacetime itself. General relativity allows spacetime to expand, contract, and curve. These changes are not constrained by the same rules as motion within spacetime. As a result, the universe can grow in ways that appear faster than light without breaking any fundamental law. This realization opens the door to a different way of thinking about faster-than-light travel. Instead of imagining a ship accelerating ever faster through space, one might ask whether space itself could be arranged to do the work. If distances can expand, perhaps they can also contract. If the universe can stretch, perhaps it can fold. This is where the strange ideas begin to gather. Wormholes, warp metrics, and other exotic solutions to Einstein's equations emerge from the mathematics not as science fiction inventions, but as legitimate, if highly speculative, possibilities. They are not guaranteed to exist in nature, but they are not forbidden outright either. A wormhole, in its simplest description, is a shortcut through space-time. Instead of travelling the long way between two distant points, one could pass through a tunnel that connects them directly. Locally, the traveller never exceeds the speed of light. They simply take a shorter route. From the outside, however, the trip appears to happen faster than light could have crossed the normal distance. This idea respects the local speed limit while producing a global effect that looks faster than light. It is one of the clearest examples of how geometry can change the meaning of distance without violating causality in any simple way. That said, wormholes come with enormous caveats. The equations that describe them typically require exotic conditions, such as negative energy densities which may or may not be physically realizable. Another strange corner appears in discussions of cosmic inflation, a brief period early in the universe's history when space expanded at an extraordinary rate. During inflation, regions of space that were once extremely close were rapidly driven far apart. The expansion was so rapid that distances increased faster than light could cross them. Again, no object outran light locally. Space itself was changing. Inflation is not a fringe idea. It is one of the leading explanations for why the universe looks the way it does on large scales. Its success lends credibility to the notion that spacetime can behave in dramatic ways under the right conditions. If the universe once expanded in this fashion, it raises the question of whether similar processes could occur again, perhaps on smaller scales or under engineered conditions. Then there are quantum effects, which introduce a different kind of strangeness. Quantum mechanics is notorious for producing correlations that seem to ignore distance altogether. Entangled particles, once linked, exhibit correlations instantly, no matter how far apart they are separated. Measure one, and the state of the other is immediately determined. At first glance, this looks like faster-than-light communication, but careful analysis shows that no usable information is transmitted in this process. The outcomes are correlated, but random. You cannot control the result on one side to send a message to the other. Causality remains intact, even though the correlations defy classical intuition. Still, entanglement reveals that the universe does not always behave in strictly local ways. Connections can exist that are not mediated by signals travelling through space in the usual sense. While this does not allow faster-than-light messaging, it hints that space-time locality may not be as fundamental as it appears. Another often cited oddity involves so-called phase velocities and group velocities in wave mechanics. Under certain conditions, the phase of a wave can move faster than light, and wave peaks can appear to propagate superluminally. These effects are real and measurable. However, they do not carry information faster than light. The underlying signal, the part that could be used to transmit a message, still respects the speed limit. These examples illustrate an important pattern. Whenever something seems to exceed the speed of light, a closer look reveals that the rules have not been broken. Either no information is being transmitted, or the effect arises from geometry rather than motion, or the apparent speed is a misinterpretation of what is actually moving. This pattern has led physicists to a cautious stance. The universe allows many surprising behaviours, but it is remarkably consistent in preserving causality. Faster-than-light effects, when they appear, are carefully constrained. They do not permit paradoxes, time loops, or contradictions in cause and effect. Even so, the existence of these strange corners matters. They show that the speed of light limit is not a blunt instrument. It is a nuanced feature of space-time that interacts with geometry, quantum mechanics, and cosmology in subtle ways. Understanding those interactions is key to knowing whether faster-than-light travel is absolutely impossible or merely extraordinarily difficult. One reason these ideas remain speculative is that they often require conditions far beyond anything we can currently achieve. Negative energy, for example, appears in quantum theory in limited forms, such as the Casimir effect, but not in the quantities needed to stabilize a wormhole or generate a warp-like geometry. The gap between theoretical allowance and practical realization is enormous. There is also the question of stability. Many exotic solutions to Einstein's equations are mathematically valid, but physically fragile. Small perturbations can cause them to collapse, pinch off, or become unworkable. Nature may allow them on paper while preventing them from existing in practice. Another consideration is self-consistency. Some faster-than-light scenarios lead inevitably to time travel, whether intended or not. Once faster-than-light motion is combined with relativity, closed loops in time can emerge. This raises the spectre of paradoxes, which physics has so far been very good at avoiding. Some theorists suspect that unknown principles prevent such situations from ever arising, even if the equations seem to allow them. Despite all of this, the strange loopholes hidden in physics serve an important purpose. They remind us that our understanding of space-time is incomplete. The theories we rely on work extraordinarily well within their tested domains, but they leave open questions at their edges. Those questions are not invitations to abandon rigor, they're invitations to refine it. It is also worth noting that physics does not proceed by declaring things impossible lightly. Throughout history, ideas once thought forbidden have become accepted as understanding deepened. That does not mean faster-than-light travel will join that list, but it does mean the question deserves careful, patient exploration rather than dismissal. As these loopholes are examined, a recurring theme emerges. Directly outrunning light through space remains firmly prohibited for objects with mass. But manipulating space-time itself, changing distances rather than speeds, occupies a different category. Whether that category contains anything physically realizable is still an open question. What matters for now is recognizing that the speed of light limit, while robust, is not simplistic. It does not banish all imaginative possibilities. It shapes them, channels them, and forces them into forms that respect deeper principles. When the speed of light refuses to be outrun, the natural response is not always to give up but to rethink the route. If motion through space is constrained, perhaps the more interesting question is whether space itself is as rigid as it seems. This line of thinking does not come from impatience or a desire to cheat the universe. It comes directly from taking Einstein's ideas seriously and following them to their logical, if unsettling, conclusions. If space and time are flexible, if they respond to energy and motion, then perhaps the problem is not how fast something moves, but how far it actually has to go. In everyday life, distance feels absolute. A kilometre is a kilometre, whether you walk it, drive it, or fly over it. The effort changes, the time changes, but the distance itself remains fixed. This intuition is so deeply embedded that it's difficult to imagine distance as anything other than a static feature of reality. Yet general relativity tells a different story. Distance is not merely a backdrop. It is a dynamic quantity, shaped by mass, energy, and the geometry of space-time. Gravity itself is the first hint of this flexibility. Objects do not fall because they are pulled by an invisible force in the classical sense. They follow curved paths through space-time that has been distorted by mass and energy. The Earth bends the space-time around it, and objects move along the straightest possible paths within that curved geometry. What feels like a force is really geometry guiding motion. Once this idea is accepted, the possibility of manipulating geometry becomes at least conceptually imaginable. If mass and energy can curve spacetime unintentionally, could sufficiently advanced control of those ingredients curve it deliberately? Could space be shaped in such a way that the distance between 2 points shrinks, even temporarily, without anything locally moving faster than light? This is the core idea behind warp-based approaches to faster-than-light travel. Instead of pushing a spacecraft through space at extreme speeds, the surrounding spacetime would be altered so that the craft remains locally at rest while space itself does the moving. In front of the craft, space would contract. Behind it, space would expand. The craft would ride this distortion, carried along without ever exceeding the speed of light in its immediate environment. From the inside, nothing extraordinary would happen. The craft would not experience enormous accelerations. Clocks would tick normally. Light inside the ship would behave as expected. Locally, all the familiar rules of physics would remain intact. From the outside, however, the craft would appear to traverse vast distances in remarkably short times, potentially faster than light could travel through undistorted space. What makes this idea compelling is that it does not attempt to violate the local speed limit. It respects the cosmic speed bump by going around it rather than over it. The trick, if it can be called that, lies entirely in the geometry. The most famous formalization of this concept appeared in the mid-1990s, when a specific solution to Einstein's equations was proposed that described exactly this kind of spacetime distortion. The mathematics showed that such a geometry was not forbidden by general relativity. In principle, spacetime could be arranged into a bubble that moves arbitrarily fast relative to distant observers while remaining locally consistent. At first glance, this sounds like a breakthrough, a way to reconcile faster-than-light travel with the strictures of relativity. But as with most things in physics, the devil is not just in the details. It is in the assumptions. The geometry required for such a warp arrangement is not something that can be produced with ordinary matter or energy. It requires regions of space-time where the energy density is negative. This is not just unusual. It runs counter to the behavior of most known forms of matter and energy, which have positive energy density. Negative energy is not entirely alien to physics, but it appears only in very limited, highly constrained quantum effects. Even when negative energy does appear, it does so fleetingly and in tiny amounts. Scaling it up to macroscopic levels, shaping it, stabilizing it, and sustaining it over time is an entirely different challenge. The equations may allow such configurations, but the universe may be extremely reluctant to provide the necessary ingredients. There is also the question of control. Warping spacetime in this way would require precise manipulation of energy distributions on scales that dwarf anything humans currently handle. The slightest imbalance could collapse the geometry or produce unintended effects. This is not like building a faster engine or a stronger hull. It is more like attempting to sculpt the fabric of reality itself with atomic precision. Another issue is that while the craft inside the warp bubble would not experience high accelerations, the spacetime around it would be undergoing extreme curvature. The boundary between the warped region and normal space could involve enormous gradients in energy and geometry. How matter and radiation would behave at that boundary remains an open question. Would particles pile up? Would radiation accumulate? Would the bubble be stable, or would it shed energy in unpredictable ways? Then there is the problem of causality. Even though local speeds remain subliminal, the global effect of warp travel can still lead to causal paradoxes. If a warp bubble can move faster than light relative to distant observers, it becomes possible, in principle, to construct scenarios where cause and effect loop back on themselves. The same issues that plague direct faster-than-light travel reappear in a more subtle form. Some physicists suspect that unknown principles prevent these geometries from being realized precisely because of these issues. The equations of general relativity allow many solutions that are mathematically consistent but physically unattainable. They describe what spacetime could do in theory, not necessarily what it will do in practice. There is also the question of how a warp configuration would begin and end. Creating a region of contracted space in front of a craft implies that something must cause that contraction before the craft arrives. Similarly, expanding space behind the craft implies a causal influence extending outward. How these changes propagate without violating causality is not fully understood. Even setting aside these challenges, the energy requirements alone are staggering. Early estimates suggested that the amount of energy needed to create a warp bubble of modest size would exceed the mass energy of entire planets or stars. Later refinements reduced these estimates somewhat, but they remain far beyond any realistic capability. The numbers are not just large, they are cosmically large. Despite this, research into warp-like geometries has not stopped. Part of the reason is that exploring these ideas teaches us something valuable, even if they never become practical. They force physicists to confront the limits of general relativity, the role of energy conditions, and the interplay between geometry and causality. They highlight where our theories are flexible and where they resist change. Another reason is that our understanding of energy itself may be incomplete. Quantum field theory already allows for effects that would have seemed impossible in classical physics. Vacuum energy, zero-point fluctuations, and subtle quantum inequalities complicate the picture of what energy can do. It is not impossible that future insights could reveal new ways of arranging energy and space-time that we do not currently foresee. Still, it is important to remain grounded. Warping space instead of breaking the rules does not magically make faster-than-light travel easy or likely. It relocates the difficulty rather than eliminating it. The speed limit is respected, but the cost is paid in geometry, stability, and energy. There is also a philosophical shift embedded in this idea. Travel becomes less about movement and more about topology. Instead of crossing space, one reshapes it. Instead of racing through the universe, one rearranges the universe so that the destination comes closer. This is a radical departure from how motion is usually conceived. From a human perspective, this can feel almost unsettling. We are accustomed to the idea that effort correlates with distance. You go farther by moving longer or faster. Warp-based ideas break that intuition. Distance becomes negotiable. The universe becomes malleable in ways that challenge everyday experience. At the same time, these ideas underscore how deeply geometry governs reality. If such manipulation were ever possible, it would not represent a triumph over physics, but an intimate collaboration with it. One would not be breaking the rules, but using them in their most extreme form. As the discussion continues, it becomes clear that warping space is not a loophole in the casual sense. It is an extrapolation. It takes the core insight of general relativity, that space-time is dynamic, and asks how far that dynamism can be pushed before the theory breaks or new principles intervene. This naturally leads to further questions. If space can be warped to create shortcuts, could it also connect distant regions directly? Could space-time fold in on itself, creating tunnels rather than bubbles? If warping space suggests stretching and squeezing the universe like a slow, deliberate breath, then wormholes suggest something even more radical, folding it over itself. Instead of changing how long a journey takes, wormholes propose changing what a journey even means. They replace the idea of crossing vast distances with the idea of stepping through a shortcut, one that connects two faraway regions of space and time as though they were neighbours. It's a concept that feels intuitive on a map, but deeply strange when applied to reality itself. To understand why wormholes appear in physics at all, it helps to start with how distance normally works in curved space-time. In general relativity, the distance between 2 points is not fixed by coordinates alone. It depends on the geometry of space-time between them. Curvature can make paths longer or shorter than they would be in flat space. This is already familiar in a mild way. On the surface of the Earth, the shortest path between two cities is not a straight line on a flat map, but a curved arc following the planet's surface. Geometry matters. Now imagine taking that idea to its extreme. Instead of gently curving space, imagine folding it so sharply that two distant regions touch, not metaphorically, but geometrically. In that case, a path that looks impossibly long when measured through ordinary space could become trivially short through the fold. A traveller would not be moving faster than light through space. They would simply be taking a route where the distance itself is drastically reduced. This is the essence of a wormhole. It is not a tunnel dug through space in the everyday sense. It is a feature of space-time geometry that connects two separate regions through a narrow bridge. The distance through the bridge can be very short, even if the distance outside it is enormous. From the outside, the two ends of the wormhole might appear light years apart. From the inside, they could be separated by only moments of travel. The mathematics of general relativity allow such structures. In fact, the equations describing gravity naturally admit solutions that resemble wormholes. Some of these solutions were discovered early in the development of the theory, long before science fiction embraced the idea. They were initially viewed as curiosities, artifacts of the mathematics rather than serious physical possibilities. One of the earliest examples involves what is sometimes called a bridge between two regions of space-time. In its simplest form, this bridge is unstable. It pinches off too quickly for anything to pass through. It exists only as a fleeting geometric feature, not a usable shortcut. This instability is not a minor inconvenience. It reflects a deeper issue. Gravity, as we normally experience it, tends to pull things together. Keeping a passage open against that tendency requires something unusual. This brings us back to a recurring theme. Exotic geometry demands exotic energy. For a wormhole to remain open long enough for travel, the space-time around its throat must behave in a way that counteracts gravitational collapse. That behaviour typically requires negative energy density, the same problematic ingredient that appears in warp-based ideas. Negative energy is not just a matter of having less energy. It is a specific violation of conditions that normally hold in classical physics, conditions that ensure energy densities are positive and gravity behaves predictably. In quantum theory, negative energy can appear in limited contexts, but it is constrained in magnitude, duration, and distribution. These constraints make it extremely difficult to scale up negative energy effects to macroscopic structures. Even if such energy could be produced and arranged, there are further complications. A wormhole has two mouths, two openings into ordinary space-time. Their locations are not fixed by the wormhole itself. They could, in principle, be moved relative to one another. This mobility introduces a new layer of strangeness. If one mouth of a wormhole were accelerated to high speed or placed in a strong gravitational field while the other remained relatively stationary, time dilation effects would cause the two mouths to age differently. This difference would turn the wormhole into a time machine. Entering one mouth could lead to exiting the other at an earlier time. This outcome is not an added feature. It follows directly from combining wormhole geometry with the same time dilation effects discussed earlier. The result is that traversable wormholes almost inevitably allow backward time travel, unless some additional principle intervenes. This is where concerns about causality become unavoidable. Time travel introduces paradoxes, not just philosophical puzzles, but logical contradictions that threaten the consistency of physical law. While there are proposed resolutions, such as self-consistency principles or branching timelines, none are universally accepted. The mere appearance of these issues raises suspicion that something fundamental is being overlooked. Some physicists take this as a sign that traversable wormholes are forbidden by deeper laws not yet fully understood. Others see it as a challenge, an indication that our understanding of time, causality, or quantum gravity is incomplete. The equations of general relativity are classical. They do not account for all quantum effects. Perhaps those effects enforce consistency in ways we do not yet see. There is also the question of formation. Even if a stable wormhole could exist, how would it come into being? Would it form naturally, perhaps in extreme environments like the early universe or near black holes? Or would it require deliberate construction, an act of engineering so advanced that it borders on the unimaginable? Natural formation seems unlikely under known conditions. Wormholes do not appear to arise spontaneously in simulations of cosmic evolution. They are not observed in astrophysical data. If they exist, they are either exceedingly rare, extremely small, or both. Artificial construction, on the other hand, demands control over spacetime on scales and with precision far beyond current capability. Creating a wormhole would not be like building a bridge or a tunnel. It would involve sculpting the geometry of spacetime itself, arranging energy and curvature in a precise configuration, and stabilizing it against collapse and quantum fluctuations. Even assuming such a feat were possible, practical issues remain. A wormhole throat could be extremely small, perhaps microscopic. Enlarging it to allow macroscopic objects to pass through might require enormous additional energy. The stresses at the boundary could be destructive. Radiation could accumulate. Feedback effects could destabilize the structure. Then there is navigation. A wormhole does not automatically lead where you want it to. Its endpoints would need to be positioned deliberately. Moving them through space would itself involve relativistic effects, gravitational interactions, and energy expenditures. The wormhole is not a simple door you can place anywhere. It is a complex space-time object with its own dynamics. Despite all of these challenges, wormholes remain compelling because they embody a different approach to faster-than-light effects. They do not ask anything to move faster than light through space. They ask space to be connected differently. They exploit the fact that distance is not fundamental in the way we often assume. This exploitation is not arbitrary. It follows directly from the insight that spacetime is a dynamic entity. If gravity is geometry, then geometry can, in principle, have non-trivial topologies. Space does not have to be simply connected. It can have handles, tunnels, and shortcuts, at least mathematically. Topology, the study of how spaces are connected, becomes relevant here. Two regions can be far apart in terms of distance but close in terms of connectivity. A wormhole is a topological feature, not just a geometric one. It changes how space is connected, not just how it is curved. Topology is remarkably flexible in mathematics, but physics often imposes additional constraints. Not every mathematically allowed topology corresponds to a physically realizable spacetime. The challenge is to determine which topology's nature permits. Quantum gravity, the still incomplete theory that would unify general relativity with quantum mechanics, is likely to play a crucial role in answering this question. At very small scales, spacetime may not be smooth. It may fluctuate, form transient connections, or exhibit behaviors that are averaged out at larger scales. Some speculative ideas suggest that spacetime at the quantum level could resemble a foam, with tiny wormhole-like structures constantly appearing and disappearing. If such structures exist, they are almost certainly microscopic and unstable, but their existence could hint that space-time connectivity is more flexible than classical intuition suggests. Scaling such effects up to macroscopic wormholes would be an entirely different challenge, but the possibility keeps the idea from being dismissed outright. Another angle comes from information theory. In recent years, connections have been drawn between quantum entanglement and space-time geometry. Some researchers propose that entanglement itself might give rise to geometric connections resembling wormholes, though not in a way that allows travel or communication. These ideas are still developing, but they suggest deep links between connectivity, information, and geometry. What matters for the broader question of faster-than-light travel is not whether wormholes are likely or practical, but what they reveal about the structure of physical law. They show that the speed of light limit is not simply about velocity. It is about how space-time is connected and how causality is preserved. Wormholes respect the local speed limit while threatening global causal order. They demonstrate that respecting one principle does not automatically preserve all others. This tension is instructive. It suggests that the universe may enforce consistency through multiple overlapping constraints, not all of which are captured by any single theory. From a storytelling perspective, wormholes feel appealing because they align with human intuition about shortcuts. We understand maps, tunnels, and folding. Translating those ideas into spacetime feels natural, even if the execution is fantastical. Physics tempers that appeal with caution, but it does not erase it. As the discussion continues, wormholes occupy an important position. They are more extreme than warping space smoothly, but less direct than outrunning light. They sit in the middle ground where geometry, topology, and causality collide. Whether wormholes exist, can be stabilized, or can ever be used is still unknown. What is clear is that their presence in the equations forces us to confront uncomfortable questions about time, cause, and the limits of physical law. They remind us that faster-than-light travel is not just about speed, it is about the structure of reality itself. Every so often, physics produces a result that sounds, at least on the surface, like a quiet rebellion against its own rules. Not a dramatic overthrow, not a clear violation, but something that makes you pause and ask whether the speed limit you thought was absolute is being bent in some subtle way. Over the years, a number of particles and phenomena have earned a reputation for doing exactly that, appearing to flirt with, skirt around, or momentarily challenge the idea that nothing can outrun light. These cases are often described with headlines that suggest cheating, breaking, or bypassing the cosmic limit. The reality, as usual, is both more restrained and more interesting. To understand why certain particles seem suspicious in this way, it helps to recall how speed is actually measured in physics. Speed is not an intrinsic label attached to an object. It is always defined relative to something else. A particle's speed is measured with respect to a particular reference frame, over a particular distance, and during a particular interval of time. When distances become extremely small and interactions extremely brief, intuition can start to wobble. This is the regime where particles live. One of the most commonly cited examples involves particles that travel very close to the speed of light, so close that the distinction between almost and equal becomes practically meaningless at first glance. Neutrinos fall squarely into this category. These particles are extraordinarily light, electrically neutral, and famously elusive. Trillions of them pass through your body every second without leaving a trace. Because they interact so weakly with matter, they can travel vast distances without slowing down in any conventional sense. Neutrinos are produced in enormous numbers by the Sun, by nuclear reactions in stars, by supernova explosions, and by particle accelerators on Earth. When they are detected, they are often travelling at speeds so close to the speed of light that the difference is almost impossible to measure directly. This has occasionally led to experimental results that appear to suggest neutrinos arriving earlier than expected. Sometimes even earlier than light would have arrived if it followed the same path. Such results tend to generate excitement, followed quickly by scrutiny. In one well-known case, an experiment reported neutrinos arriving slightly sooner than light would have, given the known distance and timing. For a brief moment it looked as though the speed limit might have been violated. The scientific community responded not with celebration, but with caution. Extraordinary claims require extraordinary verification. It did not take long for the anomaly to be traced to a mundane source. A faulty cable connection and a miscalibrated timing system were enough to account for the discrepancy. Once corrected, the neutrinos obediently fell back below the speed of light, where theory said they should be. This episode did not reveal a crack in relativity. It revealed how delicate these measurements are and how easily small technical issues can masquerade as revolutionary physics. Neutrinos remain interesting, but not because they break the speed limit. They are interesting because they approach it so closely. Their tiny mass allows them to move at speeds that differ from light speed by a vanishingly small fraction. This makes them excellent probes of relativistic effects, but it does not make them exceptions. Another class of apparent offenders comes from the world of wave phenomena. In wave mechanics, speed is not always a single, simple quantity. There is the speed at which a wave's peaks move, the speed at which energy travels, and the speed at which information is transmitted. These are not always the same. Phase velocity is the speed at which a particular phase of a wave propagates, such as the crest of a wave. Under certain conditions, phase velocity can exceed the speed of light. This sounds dramatic until you examine what is actually moving. The phase itself does not carry energy or information. It is a pattern, not a signal. You cannot use a superluminal phase velocity to send a message faster than light. Group velocity, on the other hand, is associated with the movement of a wave packet. The envelope that carries energy and information, group velocity, respects the speed of light limit. Even in systems where phase velocity exceeds light speed, the group velocity remains safely below it. There are also situations where the peak of a wave packet appears to move faster than light, or even emerge from a medium before it fully enters. These effects arise from the reshaping of the wave packet as it interacts with the medium. The peak that emerges is not the same peak that entered. No information has travelled faster than light. The apparent violation comes from how waves interfere and reorganize themselves. These subtleties are not loopholes so much as reminders that intuition built on solid objects does not always transfer cleanly to waves. When physicists say that nothing can travel faster than light, they mean that no causal influence, no information, no energy transfer can exceed that speed. Patterns and correlations can behave in more flexible ways without threatening causality. Quantum mechanics introduces another layer of apparent speed cheating. Entangled particles exhibit correlations that appear to be instantaneous, regardless of distance. Measure one particle, and the state of its partner is immediately determined, even if they are separated by light years. This phenomenon has been tested repeatedly and confirmed beyond reasonable doubt. It is not a measurement error, it is a genuine feature of quantum theory. Yet it does not allow faster-than-light communication. The outcome of each measurement is random. You cannot choose the result on one side to control the outcome on the other. The correlations become apparent only when the results are compared, and that comparison requires classical communication limited by the speed of light. Entanglement challenges classical ideas about locality, but it leaves causality intact. Nothing useful outruns light. What changes is how we think about separation and connection at the quantum level. The universe appears to be less locally compartmentalized than classical physics assumed, but not in a way that permits signaling faster than light. There have also been speculative proposals involving hypothetical particles known as tachyons, which would, by definition, travel faster than light. Tachyons arise naturally in certain mathematical extensions of relativistic equations. They are not introduced as practical objects, but as solutions that exist if certain assumptions are relaxed. The problem with tachyons is not merely that they would be fast, it is that their existence would destabilize the theory. They would lead to runaway processes, negative energies, and violations of causality. For this reason, tachyons are generally interpreted not as real particles, but as indicators that a particular theoretical model is unstable or incomplete. When tachyon-like terms appear, they usually signal that the system wants to settle into a different state where the instability disappears. In other words, tachyons do not represent particles racing faster than light through the universe. They represent a warning sign that the mathematical description needs to be reconsidered. There are also astrophysical observations that can give the impression of superluminal motion. In some distant galaxies, jets of material ejected from the vicinity of black holes appear to move faster than light when observed from Earth. This effect is striking in images and animations, and it has been carefully studied. The explanation lies in geometry and perspective. When an object moves at a speed close to that of light, and nearly toward the observer, the light it emits at different points along its path reaches the observer in a compressed time interval. This can make the motion appear faster than it really is. The object itself never exceeds the speed of light. The illusion arises from how light travel time combines with the object's motion. These apparent superluminal motions are a beautiful demonstration of how relativity can fool intuition without breaking its own rules. They remind us that observation is not always a straightforward window into reality. It is filtered through finite signal speeds and geometric effects. Even in particle accelerators, where particles are pushed to extraordinary energies, nothing crosses the forbidden threshold. Protons and electrons can be accelerated until they are moving at 99.9999% of the speed of light, but never beyond. The closer they get, the more energy is required for smaller and smaller gains. The speed limit asserts itself not with drama, but with mathematical inevitability. What all these examples have in common is that they initially sound like exceptions, but ultimately reinforce the same principle. The speed of light is not a naive limit that can be casually sidestepped. It is woven into how information, energy, and causality are defined. When particles appear to cheat, it is usually because we are misinterpreting what is moving, how it is measured, or what kind of influence is actually being transmitted. Once those details are clarified, the apparent rebellion dissolves into consistency. This consistency is not boring, it is remarkable. The same limit holds across an enormous range of scales, from subatomic particles to entire galaxies. It survives scrutiny from experiments that push precision to extremes. It remains intact even as theories grow more sophisticated. At the same time, these near misses and apparent violations play an important role. They test the robustness of our understanding. They force physicists to refine definitions, improve measurements, and confront uncomfortable questions. They act as stress tests for theory. They also keep curiosity alive. Each time something seems to move too fast, it invites a closer look. That closer look almost always deepens understanding, even when it closes the door on a hoped-for shortcut. It becomes clear that faster-than-light travel is not thwarted by a single rule, but by a network of mutually reinforcing principles. When one angle appears promising, another closes. When one effect looks permissive, another restores balance. This does not mean the universe is hostile to exploration. It means it is consistent, and consistency, once understood, can be worked with, even if it cannot be bypassed. If matter and signals cannot outrun light, what about information itself? Is information bound by the same limits, or does it obey a different set of rules altogether? When the conversation shifts from particles racing through space to information itself, the tone of physics changes. Speeds become less about motion and more about relationships. Distances begin to feel negotiable in ways that don't involve engines, trajectories, or even paths in the usual sense. This is the realm where quantum mechanics speaks most softly and most strangely, offering hints of instant connection without ever quite allowing instant communication. At the heart of this strangeness lies a simple but unsettling observation. In the quantum world, systems can become linked in such a way that they no longer behave as independent objects, even when separated by vast distances. Their properties are correlated. Measure one, and the other responds, not after a delay that shrinks with better instruments, but apparently at the same moment. This is not a rare edge case. It is a fundamental feature of quantum theory, confirmed repeatedly by experiments of increasing precision. This phenomenon is known as entanglement, but the name itself does not explain much. It suggests a knot or a tangle, which is not entirely wrong, but it risks implying a physical connection like a string or signal. Nothing of that sort exists. There is no hidden thread stretching across space, no invisible messenger darting faster than light. The connection is not mediated by anything moving between the particles after they are separated. To understand why this feels like a whisper rather than a shout, it helps to be clear about what entanglement does and does not allow. When two particles become entangled, their combined state is described by a single quantum object. Individual properties do not have definite values on their own. Only the relationship between the particles is well defined. When a measurement is made on one particle, the combined state updates, and the outcome of a corresponding measurement on the other particle becomes determined. From a classical perspective, this looks like information travelling instantaneously. One measurement seems to tell the other particle what to do, but this interpretation sneaks in an assumption that does not hold. It assumes that the outcome of the first measurement was freely chosen and then transmitted. In reality, the outcome is random. You do not get to decide which result you obtain. Because of this randomness, entanglement cannot be used to send a message. You cannot encode information in your choice of outcome. No matter what you do, the statistics on the other side remain the same, until the results are compared using ordinary communication, which is limited by the speed of light. This limitation is formalized in what physicists call the no-signaling principle. It states that quantum mechanics does not allow faster-than-light communication, even though it allows correlations that appear instantaneous. This principle is not an extra rule pasted on to save relativity. It emerges naturally from the structure of the theory. The distinction between correlation and communication is subtle but crucial. Correlation means that outcomes are related in a predictable way when compared. Communication means that one party can influence the outcome observed by another in a controlled way. Entanglement gives you the former without the latter. Still, the existence of instantaneous correlations is deeply unsettling if one expects all influences to propagate through space over time. It suggests that the universe does not always respect classical ideas of locality. Something about the quantum description allows distant events to be connected without a mediating signal. Einstein famously disliked this aspect of quantum mechanics, referring to it as spooky action at a distance. His discomfort was not emotional, it was principled. He worried that such non-local behaviour conflicted with the spirit of relativity, even if it did not allow direct violations of causality. He suspected that quantum mechanics was incomplete, that hidden variables might restore a more local picture. Decades of experiments have tested this suspicion. The results have consistently favoured quantum mechanics. Attempts to explain entanglement using local hidden variables fail. The correlations observed in experiments exceed what any local theory can produce. This does not mean that signals travel faster than light. It means that the underlying description of reality does not fit neatly into classical categories of cause and effect. This realization has led some physicists to suggest that space-time itself may not be fundamental. Instead, it could be an emergent structure, arising from deeper quantum relationships. In this view, entanglement is not something that happens within space. It is something from which space itself might arise. This is a radical idea, but it is not idle speculation. In certain areas of theoretical physics, particularly in attempts to understand quantum gravity, strong links have emerged between entanglement and geometry. Mathematical relationships suggest that the way quantum systems are entangled can determine the shape and connectivity of space-time at larger scales. From this perspective, instantaneous correlations are not violations of a space-time-based speed limit. They operate at a level where space-time is not yet the primary organizing principle. The speed of light governs how signals move within space-time, but entanglement may reflect a deeper layer where, within and between, have different meanings. This does not suddenly make faster-than-light travel possible, it shifts the question. If space-time itself emerges from quantum relationships, then manipulating those relationships could, in principle, alter how distance and separation manifest. Whether that can ever be done in a controlled macroscopic way is entirely unknown. It is also important not to overstate what entanglement implies. Despite its non-local character, it has proven remarkably well behaved. It refuses to enable paradoxes. It respects causality in practice, even if it challenges classical intuition about how causality should work. One way to think about this is that entanglement spreads information about correlations, not about events. The universe knows how outcomes are related, but it does not reveal specific outcomes until measurements are compared. That comparison requires ordinary communication with all the familiar delays. This separation preserves the operational structure of physics. Experiments remain reproducible. Predictions remain consistent. No observer gains the ability to affect distant events instantaneously in a way that would undermine cause and effect. At the same time, entanglement has become a practical resource. Technologies such as quantum cryptography and quantum computing rely on it. In these applications, entanglement is not used to send messages faster than light, but to coordinate outcomes in ways that would be impossible classically. Security and computational advantages emerge not from speed, but from structure. This practical success underscores an important point. The quantum world is not vague or mystical. It is precise. Its strangeness lies not in unpredictability, but in predictability of an unfamiliar kind. Correlations are exact. Constraints are strict. The whisper is quiet, but it is consistent. When entanglement is discussed in the context of faster-than-light travel, it often serves as a reminder that not all connections are mediated by motion. Some relationships exist without traversal. This does not mean they can be harnessed to move matter or messages instantly. It means that the universe allows coordination without exchange. There is also a psychological element here. Humans tend to equate connection with communication, and communication with signaling. Entanglement breaks that chain. It shows that connection does not require a courier. Two systems can be part of a single description even when separated. This challenges the intuition that space necessarily separates. At the quantum level, separation is more subtle. Distance still matters for interactions and measurements, but it does not fully define relational structure. This insight feeds back into earlier discussions of wormholes and warped space. Some speculative ideas suggest that entanglement and wormholes may be two sides of the same coin, mathematically related descriptions of connectivity. In these ideas, entanglement does not allow travel or messaging, but it reflects a geometric connection at a deeper level. Even if these ideas turn out to be incomplete or incorrect, they highlight an important theme. Faster-than-light effects, when they appear, tend to involve rethinking what distance, connection, and influence mean, rather than simply pushing objects faster. Quantum whispers are not loopholes that let information escape the speed limit. They are reminders that the speed limit applies within a framework that may itself be emergent. That framework works extraordinarily well at macroscopic scales, but it may not be the deepest layer of reality. Still, the practical consequences remain unchanged. You cannot use entanglement to call a friend across the galaxy instantly. You cannot send warnings to the past. You cannot coordinate actions faster than light allows. The universe remains stubbornly resistant to such uses. What quantum mechanics offers instead is a different kind of insight. It shows that limits can coexist with surprising forms of connection. It reveals that the structure enforcing the speed of light limit is compatible with non-local correlations, provided they do not carry controllable information. This coexistence is not accidental. It suggests that the universe is organized to preserve consistency above all else. Where one principle might threaten another, constraints tighten to prevent contradiction. Every apparent opening toward faster-than-light effects is paired with a mechanism that prevents causal breakdown. The universe allows strangeness, but not chaos. Once the discussion moves away from abstract possibility and into the realm of practical consequence, the tone shifts again. Ideas that feel tantalizing when written as equations begin to acquire weight, literally. Energy enters the picture not as a convenient variable to be adjusted, but as a stubborn accounting system that refuses to be ignored. Physics, at this stage, stops asking whether something is allowed in principle, and starts asking what it would cost to make it happen. That question, more than any philosophical objection, is where most faster-than-light dreams begin to thin out. Energy is not just fuel, it is the currency of change. Every process that alters motion, shape, temperature, or geometry draws from it. In everyday life, the amounts involved are manageable. You burn calories to walk, you burn fuel to drive, you draw electricity to power a device. These exchanges are so familiar that energy feels abundant, something to be optimized rather than questioned. On cosmic scales, however, energy becomes a very different kind of constraint. To appreciate how severe this constraint is, it helps to recall how energy behaves as speed increases even before reaching exotic regimes. In classical mechanics, energy increases smoothly with speed. Double the speed, and the kinetic energy increases by a predictable factor. This relationship encourages the intuition that speed is something you can buy with enough fuel. Faster means more energy, but still within a linear negotiable framework. Relativity dismantles that intuition. As an object approaches the speed of light, its kinetic energy does not merely increase, it accelerates toward infinity. Each additional increase in speed demands more energy than the last, and the curve becomes steeper and steeper. By the time an object is moving at a significant fraction of light speed, the energy required for further acceleration is already enormous. Approaching the limit, the numbers become absurd. This alone rules out direct faster-than-light travel for massive objects in any practical sense. There is no clever engineering solution to an infinite energy requirement. It is not a matter of efficiency or materials, it is a mathematical wall. But even if one avoids direct acceleration and turns to geometric approaches like warp configurations or wormholes, energy does not step aside politely. It returns with a vengeance, wearing a different mask. In warp-based scenarios, the challenge is not accelerating a ship, but reshaping space-time around it. That reshaping requires energy. Not just a lot of energy, but energy arranged in very specific ways. Early calculations of such configurations suggested energy requirements comparable to the mass energy of entire stars or even galaxies. Later refinements reduced those estimates, but they remain staggeringly large. To put this into perspective, consider the total energy output of human civilization over its entire history. It is negligible on cosmic scales. Even the most optimistic projections of future energy production fall short by orders of magnitude. The gap between what is theoretically required and what is practically available is not incremental. It is astronomical. There is also the issue of energy density. It is not enough to have a large total amount of energy. It must be concentrated and shaped. Space-time responds not just to how much energy exists, but to how it is distributed. Creating regions of extreme curvature requires extreme concentrations. Nature achieves this in places like black holes, where matter is compressed to extraordinary densities. Reproducing anything remotely similar deliberately is beyond current imagination. Then there is the matter of negative energy, a recurring requirement in many faster-than-light proposals. Negative energy is not simply energy with a minus sign. It represents regions where the energy density is lower than that of empty space. In classical physics, such regions do not exist. Energy densities are positive or zero. Quantum physics allows for small temporary violations of this condition, but it tightly restricts their magnitude and duration. Quantum field theory places limits on how much negative energy can exist and for how long. These limits are not arbitrary. They are designed to prevent runaway instabilities and violations of causality. Even if negative energy can be generated in laboratory-scale effects, scaling it up to macroscopic levels appears to be prohibited by these constraints. Engineering does not operate in a vacuum of theory. It must work with what physics provides. The more a proposal relies on exotic forms of energy that cannot be produced, sustained, or controlled, the more it drifts from engineering into speculation. Control is another often overlooked cost. Suppose for a moment that the required energy could somehow be assembled. It would not be enough to turn it on and hope for the best. Space-time manipulation would require extraordinary precision. Small deviations could lead to catastrophic outcomes. Unintended curvature could crush structures, tear apart matter, or generate intense radiation. Unlike conventional engineering, where failures are often localized and limited, failures in space-time engineering could propagate unpredictably. Curvature affects everything in its vicinity. Errors would not politely confine themselves to a malfunctioning component. They would distort the environment itself. There is also the issue of stability. Many of the exotic space-time configurations that appear in equations are delicately balanced. Slight perturbations cause them to collapse or explode. Maintaining stability would require continuous control and constant energy input. This is not a set-it-and-forget-it scenario. It is more akin to balancing a pencil on its tip while standing on a moving platform. Even if stability could be maintained, there is the question of interaction with the surrounding universe. A warp region or wormhole does not exist in isolation. It interacts with external fields, radiation, and matter. How these interactions play out is not fully understood. Would interstellar dust accumulate at the boundary? Would radiation be amplified? Would the structure emit dangerous byproducts? These questions are not afterthoughts. They are central to whether such constructs could ever be used safely, even in principle. Physics does not offer guarantees here. It offers equations that describe idealized situations. Reality is always messier. Time also enters the cost calculation in a less obvious way. Creating extreme space-time configurations may require not just energy, but time. Processes that manipulate geometry could take durations comparable to the journey they aim to shortcut. If constructing a wormhole takes centuries, its value as a travel mechanism diminishes. Then there is the matter of maintenance. Any system that relies on continuous energy input must be sustained. Interruptions could be catastrophic. In ordinary engineering, systems are designed to fail safely. In space-time engineering, safe failure is not a concept that has been meaningfully defined. Another layer of cost appears when considering information and computation. Precisely controlling energy distributions on extreme scales would require monitoring and feedback systems of extraordinary complexity. The information processing demands alone could rival or exceed the energy demands. This is a reminder that energy and information are not separate currencies. They are deeply linked. It is also worth considering the indirect costs. A civilization capable of manipulating space-time on these scales would have access to energies that could easily be weaponized, intentionally or not. The distinction between transportation and destruction becomes blurry when the same technology can reshape gravity and geometry. Managing such power responsibly introduces social and ethical constraints that physics alone does not address. From a more sober perspective, one can ask whether faster-than-light travel, even if possible, would be worth the cost. If the energy required rivals stellar processes, if the engineering risks are existential, and if the benefits are primarily exploratory rather than survival critical, the trade-off begins to look unfavourable. Nature seems to offer an alternative. The universe is vast, but it is also old. Signals and matter travel slowly, but given enough time they reach extraordinary distances. Stars form, galaxies collide, and chemical complexity emerges without shortcuts. Perhaps the universe is structured to favour patience over haste. This is not a romantic argument. It is an observation about scales. Faster-than-light travel appeals strongly to human psychology because our lives are short, and our attention spans even shorter. On cosmic timescales, light speed is not especially slow. It is sufficient to build galaxies, spread elements, and allow intelligence to arise. Engineering, at its core, is about working with constraints rather than against them. The most successful technologies do not attempt to violate fundamental principles. They exploit them. Airplanes do not fight gravity. They use it. Electronics do not ignore electromagnetism. They harness it. Perhaps the ultimate constraint, the speed of light, belongs in the same category. This does not mean exploration must be abandoned. It means it must be reimagined. Slower travel encourages different strategies. Generation ships, probes, and communication networks that respect light speed delays all fit comfortably within known physics. They demand ingenuity, but not violations of principle. When energy costs are laid bare, faster-than-light travel begins to look less like a forbidden fruit and more like a mirage. The closer one approaches, the more it recedes. replaced by ever-growing demands. Physics does not slam the door. It leaves it open just enough to tempt curiosity, while placing the handle behind layers of constraint. That tension is instructive. It suggests that the universe is not merely saying no. It is asking a different question. Not can you go faster, but what are you willing to pay, and what are you willing to risk? Once speed crosses a certain conceptual threshold, it stops being about motion and starts being about order. Up to this point, faster-than-light ideas have strained engineering, energy budgets, and geometry, but they have not yet fully confronted the most fragile structure of all, the ordering of events in time. This is where the discussion becomes genuinely unsettling, not because it introduces new technical difficulties, but because it threatens something we rely on constantly without noticing. The assumption that causes come before effects, that yesterday leads to today and today leads to tomorrow, sits quietly beneath every decision we make. Faster-than-light motion does not merely challenge that assumption, it erodes it. To see why, it's necessary to move away from everyday language and toward how time actually functions in relativity. Time is not a universal ticker advancing in lockstep across the universe. It is local. Each observer carries their own measure of time, shaped by motion and gravity. Different observers can disagree about whether two events happened at the same time, and both can be correct. This is not philosophical ambiguity. It is a measurable consequence of how space-time works. At ordinary speeds, these disagreements are too small to matter. Two people in the same city do not argue about whether lunch happened before sunset. Their relative motion is negligible. Their clocks stay synchronized well enough that time feels shared. This shared feeling creates the illusion that there is a single global present, a cosmic now that everyone inhabits together. Relativity dismantles that illusion gently at first. As relative speeds increase, simultaneity begins to fracture. Events that are simultaneous for one observer are not simultaneous for another moving observer. There is no contradiction because the events are separated in space in such a way that neither can influence the other. Causality is preserved because no signal can travel between them faster than light. The speed of a light is what keeps this delicate balance intact. It acts as a boundary separating events that can be causally related from those that cannot. As long as nothing crosses that boundary, disagreements about simultaneity remain harmless. They are differences in perspective, not contradictions. Faster-than-light motion changes this entirely. Once an object or signal exceeds the speed of light, the boundary collapses. Events that were previously safely disconnected become linked in ways that scramble their temporal order. What one observer sees as cause and effect, another sees as effect and cause. There is no longer a consistent answer to the question of what happened first. This is not a philosophical discomfort, it is a structural breakdown. Physical laws are written in a way that assumes causes precede effects within each observer's frame. Prediction depends on that ordering, explanation depends on it. Remove it, and the language of physics itself begins to lose coherence. To make this concrete, imagine a message sent faster than light from one location to another. In the sender's frame, the message is sent at a certain time and received later. In another frame moving relative to the first, the same sequence of events can appear reversed. The message appears to be received before it was sent. Both descriptions are equally valid within relativity once faster-than-light travel is allowed. This reversal is not an illusion or a trick of coordinates. It has physical consequences. If the receiver can respond to the message and send a reply, that reply could arrive at the original sender before they sent the first message. A loop forms. Information travels in a closed circle through time. These loops are not merely confusing, they undermine causality. Decisions can influence themselves, outcomes can prevent their own causes. The familiar structure of time as a sequence becomes unstable. One might try to dismiss this by arguing that such scenarios are contrived or unlikely. But physics does not permit selective enforcement. If faster-than-light travel is allowed at all, these scenarios are not optional. They arise inevitably from the structure of spacetime. You cannot have faster-than-light signals without also having frames in which those signals travel backward in time. This is why physicists often say that faster-than-light travel implies time travel. The two are not separate possibilities. They are mathematically linked. Attempting to allow one while forbidding the other is inconsistent with relativity. Time travel, in turn, carries its own suite of problems. Some are familiar from fiction, but they have serious logical roots. If an effect can influence its own cause, then the system becomes underdetermined. There may be no consistent set of events that satisfies all conditions. This is not just a storytelling problem. It is a breakdown of determinism. Various proposals attempt to resolve this. One idea suggests that the universe enforces self-consistency. Events can loop, but only in ways that do not produce contradictions. Actions that would create paradoxes simply never occur. This sounds reassuring, but it introduces an implicit rule without a clear physical mechanism. It explains consistency by assuming it. Another proposal suggests that time travel creates branching timelines. Each intervention produces a new branch, avoiding contradiction. While this resolves paradoxes in principle, it dramatically complicates the ontology of the universe. It also raises questions about conservation laws, identity, and predictability. There is also the possibility that faster-than-light travel is allowed, but only in ways that cannot be used to send information. This mirrors the role entanglement plays in quantum mechanics. Correlations can be instantaneous, but messages cannot be, if faster-than-light effects existed only in this restricted sense. Causality could remain intact. However, such effects would not enable travel or communication in any meaningful way. What is striking is how robust causality appears to be. Every time physics seems to flirt with its violation, additional constraints appear. Energy conditions, stability requirements, quantum inequalities, and geometric limitations all conspire to prevent usable causal loops. This pattern has led many physicists to suspect that causality is not an accidental feature of our current theories, but a fundamental principle that any deeper theory must preserve. From this perspective, the speed of light is not just a speed limit, it is a guardian of temporal order. It ensures that the sequence of events remains consistent across frames, even when observers disagree about simultaneity. It allows time to be relative without becoming chaotic. This guardianship is subtle. The universe does not enforce causality with an iron fist. It allows time dilation, length contraction, and relativity of simultaneity. It allows clocks to disagree and observers to tell different stories about when things happened. But it draws the line at influence. No event can influence another outside its light cone. Once that line is crossed, time ceases to function as a reliable parameter. It becomes ambiguous in a way that is not merely conceptual, but operational. You cannot build predictive models in such a world because the future can reach back and alter the past. This brings us to a deeper question. Is time fundamental, or is it emergent? If time emerges from more basic processes, then perhaps causality is also emergent, a statistical regularity rather than an absolute law. In such a view, small violations might be possible under extreme conditions without collapsing the entire structure. However, even emergent phenomena can be robust. Temperature emerges from molecular motion, yet it obeys strict laws. Violating those laws requires extraordinary conditions. Time and causality may be similar. They may not be fundamental ingredients, but they could still be enforced by the collective behavior of underlying systems. Quantum gravity research hints at this possibility. At very small scales, time may not exist in the usual sense. Space-time itself may dissolve into a more abstract structure. Yet at larger scales, time reappears, governed by rules that preserve causality with remarkable fidelity. If that is the case, faster-than-light travel would not simply require bending space or harnessing exotic energy. It would require operating in a regime where the emergent order of time itself can be overridden without destabilizing everything else. That is a much taller order. There's also a human dimension to this. Our sense of identity, memory and responsibility is built on temporal order. We remember the past, act in the present, and anticipate the future. Faster-than-light effects that scramble time would undermine this structure. Events would lose their narrative coherence. Meaning itself would become difficult to maintain. This does not mean the universe cares about human psychology, but it does highlight how deeply time order is woven into complex systems. Biological processes, learning, evolution, and social organization all depend on reliable sequencing. A universe that routinely allowed causal loops might struggle to sustain complexity at all. Seen this way, the resistance to faster-than-light travel may not be an arbitrary limitation. It may be a prerequisite for a universe capable of hosting stable structures, information processing, and life. Speed limits protect not just physics, but history. This realization reframes the earlier discussion of cost. Energy and engineering challenges are formidable, but they are secondary. The primary cost of faster-than-light travel is temporal coherence. The universe appears to demand consistency in the order of events, and it enforces that demand through the geometry of space-time. None of this proves that faster-than-light travel is absolutely impossible. Physics is cautious about absolute statements, but it does explain why the burden of proof is so high. Any proposal must not only respect local speed limits and energy constraints, it must also preserve causality across all frames. As the exploration continues, this burden becomes the central theme. Faster-than-light ideas are not ruled out by a single equation or principle. They are constrained by a web of interdependent requirements that all point in the same direction. Time, space, energy, and causality form a tightly coupled system. Pull on one thread, and the others respond. The question then shifts again. If faster-than-light travel threatens time itself, could the universe allow it in some limited, carefully restricted form? Or does the consistency of time demand an absolute prohibition, one enforced not by explicit rules, but by the structure of reality? That question does not have a settled answer. What it does have is a pattern. Every time physics approaches the edge of faster-than-light possibility, it encounters the same resistance, not from conservatism, but from coherence. The universe seems willing to be strange, but not self-contradictory. The focus turns away from dramatic possibilities and toward the quieter question of principle. Even if faster-than-light travel could be described mathematically, would the universe actually allow it? Or does something deeper, something not yet fully articulated, stand guard over the flow of time, ensuring that however flexible space-time becomes, it never allows the story of cause and effect to unravel? By the time the question reaches this point, it has changed its character. It is no longer asking whether engines can be built, or whether equations can be solved, or whether clever geometries can be imagined. It is asking something quieter and more fundamental. Could the universe allow faster-than-light travel at all, even in principle, even in a form so constrained and exotic that it bears little resemblance to travel as we normally understand it? Or is there something about the structure of reality that closes every door, no matter how patiently or creatively one knocks? Physics is unusually cautious when it comes to questions like this. Absolute impossibility is a strong claim, and history offers many examples of ideas once thought impossible that later turned out to be achievable within a broader understanding. At the same time, physics is not neutral. Some possibilities are treated as more plausible than others based on how well they fit into the existing web of principles that hold everything together. To ask whether the universe could allow faster-than-light travel in principle is really to ask whether all the constraints discussed so far, the speed of light, energy requirements, spacetime geometry, quantum effects, and causality, might somehow coexist with a controlled exception. Not a violation, but an accommodation, something that works with the rules rather than against them. One way to approach this is to look at how physics treats limits in general. Some limits are contingent. They arise from particular conditions and can change if those conditions change. The boiling point of water depends on pressure. The strength of materials depends on composition. These limits invite improvement. Others appear deeper. They are tied to symmetries and conservation laws that apply universally. The impossibility of perpetual motion is one such limit. It is not a matter of engineering ingenuity. It is a consequence of energy conservation. The speed of light belongs firmly in the second category. It is not just an observed maximum speed. It is a constant that shapes the structure of physical law. It appears in electromagnetism, in relativity, and in the way spacetime is measured. It defines how causes propagate and how events are ordered. Still, physics has taught us to be careful. Even deep principles can turn out to be emergent rather than fundamental. Temperature emerges from molecular motion. Solidity emerges from electromagnetic interactions. Perhaps the speed of light is similarly emergent, a feature of space-time at certain scales, rather than an absolute law at all scales. This line of thinking leads naturally to quantum gravity, the unfinished attempt to unify general relativity with quantum mechanics. In this regime, space-time itself may not behave as a smooth continuum. It may be discrete, fluctuating, or relational in ways we do not yet fully grasp. If space-time is not fundamental, then its limits might not be fundamental either. Some approaches to quantum gravity suggest that space-time emerges from more basic entities, such as networks of quantum relationships. In such pictures, distance is not primary. Connectivity is. Two regions may be far apart in an emergent sense while being closely linked at a deeper level. This opens the conceptual door, at least slightly, to the idea that shortcuts could exist without violating deeper principles. However, even in these speculative frameworks, causality remains stubbornly protected. Models that allow radical departures from classical spacetime often impose strong constraints to prevent paradoxes. Time ordering may become fuzzy at very small scales, but it reasserts itself at larger scales where physics becomes classical. Faster-than-light effects, if they appear at all, tend to be confined to regimes that cannot be exploited for signaling or travel. This pattern is telling. It suggests that causality is not a fragile rule easily bent or broken. It may be a robust feature that emerges whenever systems are complex enough to support observers, memory, and consistent histories. Another way to frame the question is to ask whether the universe could allow faster-than-light travel without allowing time travel. If the two could be separated, the door might open a crack wider. Unfortunately, within relativity they are tightly linked. Faster-than-light travel almost always implies the existence of reference frames in which effects precede causes. Some have proposed that the universe might enforce a preferred frame of reference, one in which time ordering is absolute. This would break a core symmetry of relativity, but could, in principle, restore global causality even with faster-than-light effects. Such ideas have been explored, but they come at a significant cost. They reintroduce absolute space and time in ways that conflict with a vast body of experimental evidence. Moreover, introducing a preferred frame does not automatically solve all problems. It raises new questions about why that frame exists, how it is selected, and why its effects are not more easily observed. So far, no compelling evidence supports such a structure. Another possibility is that faster-than-light travel could be allowed only in regions of space-time that are otherwise causally isolated, preventing paradoxes from influencing the wider universe. For example, certain exotic space-time configurations might permit closed time-like curves internally, while remaining disconnected from the rest of space-time. In this scenario, causality violations would be quarantined. While intriguing, this idea remains speculative. It relies on space-time structures that are themselves poorly understood and may not be physically realizable. It also raises uncomfortable questions about determinism and predictability within those regions. There is also the notion that the universe might allow faster-than-light effects, but only in ways that are fundamentally uncontrollable. Just as quantum randomness prevents entanglement from being used for communication, perhaps any faster-than-light mechanism would be intrinsically noisy or unstable, preventing deliberate use. This would preserve consistency while allowing strangeness. The universe would not forbid faster-than-light phenomena outright, but it would prevent them from being harnessed. They would exist as curiosities rather than tools. Such a stance aligns with a broader pattern in physics. Whenever something threatens to violate a core principle, additional constraints appear. Energy conditions limit exotic geometries. Quantum inequalities limit negative energy. No signaling theorems limit quantum correlations. Each constraint does not forbid novelty, but it channels it into harmless forms. From this perspective, the universe does not say no by decree. It says no by architecture. The structure of physical law makes certain outcomes extraordinarily difficult to achieve in a controlled way. This architectural resistance is especially evident when one considers scale. Many exotic effects appear at extremely small or extremely large scales. Quantum fluctuations at the Planck scale, inflationary expansion in the early universe. At human scales, these effects average out. The world becomes stable, predictable, and causal. Faster-than-light possibilities, if they exist at all, may be confined to regimes far removed from anything that could be engineered or experienced. There is also the question of consistency over time. A universe that allows faster-than-light travel must remain stable over billions of years. It must support galaxies, stars, chemistry, and life. If faster-than-light effects tended to destabilize causality, even rarely, the long-term evolution of the universe could be chaotic. The absence of such chaos in observations suggests that whatever the ultimate laws are, they strongly suppress such behavior. This is not proof. Absence of evidence is not evidence of absence, but it is a clue. The universe we observe is remarkably well behaved across enormous scales of time and space. Its laws are consistent, its patterns repeat. Faster-than-light travel, if allowed even occasionally, would have left traces in the structure of cosmic history. Another angle comes from information theory. Information appears to be a conserved and constrained quantity. Black hole physics, for example, suggests deep links between information, entropy, and spacetime geometry. Faster-than-light information transfer would disrupt these relationships in ways that current theories struggle to accommodate. If information cannot be duplicated or destroyed arbitrarily, and if it must propagate in a controlled way, then speed limits on information flow may be more fundamental than speed limits on matter. In that case, even if matter could somehow move faster than light, information might not. Such motion would be physically meaningless, as no observer could make sense of it. At this point, the question becomes almost philosophical, but not in a loose or speculative way. It becomes about what kind of universe can support intelligibility. Physics, at its core, is about making sense of patterns. A universe that allowed unrestricted faster-than-light travel might still exist, but it might not be describable in a coherent way. It might not support stable observers capable of asking questions. This leads to a subtle but important shift. Instead of asking whether faster-than-light travel is forbidden, one can ask whether it is compatible with a universe that has consistent laws, stable structures, and meaningful histories. The answer appears to be, at the very least, unclear. None of this closes the door completely. Physics is incomplete. Quantum gravity remains unsolved. New principles may emerge that reshape how we think about spacetime and causality. It is possible that some deeply constrained form of faster-than-light behavior exists that does not unravel time. But if such a form exists, it is likely to be profoundly unintuitive. It would not look like starships leaping between galaxies. It would not resemble travel as we imagine it. It would be subtle, limited, and tightly bound to conditions we do not yet understand. In that sense, the universe's apparent resistance to faster-than-light travel is not hostile, it is instructive. It points us toward what matters most in physical law, consistency, causality, and coherence. Instead of asking whether faster-than-light travel is possible, one begins to ask what the question itself reveals about our relationship with the universe. Why does this idea captivate us so strongly? What does it say about how we experience distance, time, and limitation? As the question slowly loosens its grip, something subtle happens to the way it feels. It no longer presses forward demanding an answer. It begins to recede, not because it has been resolved, but because it has been seen from enough angles to lose its urgency. Faster-than-light travel, once a sharp idea pointing toward distant stars, becomes softer here, less about motion and more about perspective. The universe hasn't changed during this exploration, but our relationship to it has, and that shift is often quieter than the questions that prompted it. Throughout this journey, speed has been treated as a problem to be solved, a boundary to be examined, a temptation to be resisted. Yet speed itself is only one way of engaging with distance. It is the most obvious one for creatures with limited lifespans and restless minds, but it is not the only one. The universe does not seem particularly concerned with haste. It unfolds patiently, allowing structures to form, dissolve, and reassemble over spans of time that dwarf human history. Stars burn for billions of years. Galaxies drift and merge on timescales that make urgency meaningless. From that vantage point, the speed of light begins to feel less like a frustrating limit and more like a rhythm. It sets the pace at which the universe communicates with itself. It defines how quickly changes propagate, how long it takes for events to influence one another. It is fast enough to weave the cosmos into a coherent whole, yet slow enough to preserve order and sequence. This rhythm has shaped everything discussed so far. It governs the flow of information, the structure of causality, the geometry of spacetime, and the delicate balance that allows complexity to persist. Faster-than-light travel challenges that rhythm, not by asking for a faster beat, but by asking whether the beat itself can be ignored. The universe's response, so far as we can tell, has been consistent. It allows imagination to wander, mathematics to explore, and theory to stretch, but it resists any attempt to disrupt the underlying tempo. What emerges from this resistance is not a simple prohibition, but a kind of guidance. Every time physics approaches the edge of faster-than-light possibility, it encounters structures that redirect the question. Energy costs explode, stability falters, causality trembles, time begins to misbehave. These are not separate obstacles. They are facets of the same underlying coherence. This coherence is easy to overlook because it does not announce itself. It is revealed indirectly, through the way disparate parts of physics align. Relativity, quantum mechanics, thermodynamics, and information theory all point, from different directions, toward the same conclusion. Whatever the ultimate nature of reality is, it seems to prioritize consistency over convenience. That priority has consequences for how we think about exploration. Faster-than-light travel is often imagined as a solution to distance, a way to compress the universe into something more accessible. But distance is not merely an inconvenience. It is a feature that shapes experience. It creates separation, delay, anticipation, and context. Without distance, events collapse into one another. Stories lose their sequence. Meaning becomes harder to sustain. Lightspeed delays are part of how the universe tells its story. When you look at the night sky, you are not seeing objects as they are now, but as they were when their light began its journey. This delay turns observation into archaeology. It allows the past to coexist with the present in a visible way. Faster-than-light travel would erase that layering, flattening time into something less textured. There is also a practical humility built into lightspeed limits. They remind us that we are participants in the universe, not its authors. We do not get to rearrange reality arbitrarily. We engage with it on its terms. This engagement can be creative, but it is never absolute. At the same time, it would be a mistake to interpret this as discouragement. Physics is not telling us to stop asking questions. It's telling us which questions are likely to be fruitful. The exploration of faster-than-light ideas has already paid dividends, not by delivering shortcuts to the stars, but by deepening our understanding of space-time, energy and information. Warp metrics, wormholes and quantum entanglement may never become tools for travel, but they have reshaped how physicists think about geometry and connectivity. They have revealed that distance is not as fundamental as it seems, even if it remains stubbornly relevant. They have exposed links between gravity and information that were previously unimaginable. In this sense, faster-than-light travel has served as a productive impossibility. It has acted as a horizon that guides inquiry without ever being reached. Horizons are valuable that way. They give direction without offering a rival. There is also something worth noticing about how human curiosity interacts with limits. We tend to frame limits as adversaries, something to overcome, something standing between us and what we want. But many limits are generative. They shape creativity by forcing adaptation rather than brute force. Consider how flight developed. Humans did not defeat gravity. They learned to work with it, shaping airflow to generate lift. Sound barriers were not smashed by ignoring physics, but by understanding shock waves and designing around them. In each case, progress came from cooperation with constraints, not defiance. The speed of a light may belong in this category. It may not be a wall to be broken, but a boundary that encourages different forms of engagement. Communication networks that accept delay, exploration strategies that unfold over generations, observation techniques that extract meaning from ancient light. From this perspective, stillness takes on a different meaning. Stillness is not inactivity. It is alignment with a larger timescale. It is the recognition that not everything must happen quickly to be meaningful. Even within physics, stillness has a role. In relativity, being at rest is not an absolute state, but it is still meaningful locally. Each observer experiences themselves as stationary, carrying their own clock and ruler. This local stillness is what allows measurement, memory and identity to exist at all. Faster-than-light travel threatens that by dissolving the relationship between motion and time. The universe seems to value local coherence. It allows observers to inhabit their own frames without contradiction. It allows histories to accumulate without interference. This local coherence scales upward, enabling complex systems to form. Faster-than-light effects, when examined closely, tend to disrupt that coherence rather than enhance it. That disruption may be the ultimate reason such effects are so tightly constrained. A universe that permitted routine violations of temporal order might struggle to sustain complexity. Feedback loops could destabilize processes. Information could lose its meaning. Evolution itself might falter without reliable sequencing. None of this is proven. It is inferred from patterns, from what physics seems to permit and what it resists. But the inference is consistent across theories and scales. The universe behaves as though it is invested in preserving narrative order. As this exploration drifts toward stillness, the original question softens. Is faster-than-light travel actually possible? Becomes less a demand for an answer, and more a lens through which to view the universe. The answer may be no, it may be not yet, it may be yes, but only in forms that barely resemble travel at all. What matters is that the question reveals how deeply speed, time and meaning are intertwined. It also reveals something about us. Our fascination with faster-than-light travel reflects a discomfort with scale. The universe is vast and we are small. Light-speed delays remind us of that fact every time we look outward. Wanting to outrun light is, in part, a desire to make the universe feel more intimate, more responsive to human timelines. Physics does not mock that desire, it contextualizes it. It shows us that intimacy with the universe does not come from speed alone. It comes from understanding, from recognizing patterns, from seeing how limits are connected rather than isolated. In the quiet aftermath of this question, it becomes possible to appreciate the universe as it is rather than as we wish it to be. A place where information moves at a finite pace, where distance matters, where time has texture, where cause and effect form a stable scaffold for complexity. That appreciation does not end curiosity. It redirects it. Instead of asking how to get somewhere faster, one might ask how much can be learned from where one already is. Instead of imagining shortcuts, one might explore depth. As this thought settles, the universe feels less like a race course and more like a landscape. Not something to be crossed as quickly as possible, but something to be inhabited, observed, and slowly understood. The edge of possibility remains visible, but it no longer demands pursuit, and so the motion that began with speed returns to stillness, not as an ending, but as a pause, a moment where questions rest without needing immediate answers, where the universe continues at its own pace, carrying light across vast distances, preserving stories in photons, and inviting attention rather than haste. The inquiry does not stop, remaining open, unresolved, and quietly attentive to whatever the universe is willing to reveal next.